Hello, everybody. My name is Andrea Malchiodi, and I'm the current director of the De Giorgi Mathematical Research Center. So I would like to welcome you to this workshop, and I will only say a few words, so I won't take much time. So the center was founded about 20 years ago, formally as a research laboratory of Scuola Normale Superiore, but with a mission of being like a gathering point for the whole mathematical community in Pisa. So this is formed from people of Scuola Normale, but also from the University of Pisa, and there's a smaller community at Scuola Sant'Anna. And these other institutions contribute financially and crucially, especially the University of Pisa, to the activities of the center. So since the foundation, the main activities of the centers have been workshops, intensive research periods, schools, and we recently started a colloquium series. There are two types of visiting positions. There are opportunities to perform research in pairs for short visits, and we also have 2 years postdoctoral positions. I'm basically done, so I would just like to conclude thanking the organizers for bringing up this very interesting event, and also to the staff of the center for their constant and valuable support. Thank you.
Okay, so thank you, Andrea, and thank you for hosting us here. So we begin this workshop, which is, as the title suggests, on the mathematics of machine learning, and the idea is to bring together people around this subject. This is so we organized also the school last week. So some of you have been there also last week, and this will be, so the basis was last week, and now instead more advanced and research topics. So it's my pleasure to introduce you to Giuseppe Carleo from EPFL, which will begin this series of lectures. So we split into 3 series of lectures, and one of them is on machine learning for quantum physics, right? More or less. Okay. So thank you, and please.
So good morning, everybody. Thank you for being here. As it was mentioned, this is a workshop on the mathematics of machine learning. So it's quite interesting that I'm the one designated to give the introductions, since I'm not a mathematician, but I'm a physicist. But what I was trying to do this morning, at least, is to give you an overview of the main concepts that, at least in our lectures, the lecture that me and Filippo Vicentini will give during this workshop, will have this. The goal of the if you want, of these 4 or 5 lectures actually is to give you an idea of the applications of deep learning, which is a branch of machine learning, as many of you already know, I guess, to quantum physics. But before we get there, I think it's good that we establish a bit of a common background and a common formalism. Maybe some of you or most of you are already familiar with this, but I would like to give maybe also a perspective from a physicist that is a bit different, I guess, and less formal, but maybe more geared towards applications than what we've done so far, I guess. Okay, so just to give you a quick tour of this story. First, I will start maybe with giving you a few references that might be useful for those of you who want to know more. Of course, I will not have the time to cover all of deep learning, so I will especially focus on deep learning, but even in the context of deep learning, I will not be able to tell you all the details, because this will take essentially 1 semester or more. But you can have a look at these 2 books. So especially, I guess, this one is written in a language which is not too which is relatively formal, I would say, especially if you compare other books that have been written in the context of deep learning. I find this one especially, understandable if you're a physicist or I guess also a mathematician, in the sense that it tells you, it writes down at least equations. Instead, if you find other books that are written in the context of deep learning, they might be more hand-waving. So this one is, in this sense, recommended, the one by Murphy, and it's also for free. You can download it for free legally online. Now, from the software side, Filippo will tell you more about applications, practical applications of machine learning, of deep learning. It's clear that this is a computational, if you want, strategy, so you need to be able to use software to do that. Otherwise, at least in the applications, and to do this kind of applications, Filippo will tell you about JAX, which is a common language, if you want, in Python. I mean, a library written in Python that we will use also for the tutorials, some of the tutorials that Filippo will give. And then later on, I guess I will cover some of the applications of machine learning in science, and specifically in physics. So some of the connections that exist between these two words, and some of these are written in that review that we wrote in 2019. Sorry, I forgot the year there. So it's, in a sense, already outdated, since the field is moving quite fast, but it contains at least the main ideas and goals of the field. Good. So just to start this our journey, so most of you are familiar with the concept of machine learning. So I will give you my minimal description and not accurate description of what machine learning is, but to a large extent, or at least for the application that we will describe today, you can think that machine learning is a set of complicated or less complicated numerical technique, advanced numerical techniques to approximate often unknown high-dimensional functions. Okay, so we can work with this definition, at least working definition of machine learning, and then we'll see how this can be useful to analyze and solve several problems. And a special remark that I would like to say is that AI, so artificial intelligence, and machine learning in general are not synonyms, in the sense that machine learning is just a much smaller branch, if you want, of the larger field of AI, which is instead the idea of creating independent and thinking machines, whereas machine learning is a much more smaller subset of the things that you can do in this context. So this is a diagram taken from the first reference that I had in my introduction, where you can see that, for example, deep learning, which is by itself a branch of machine learning, right, is contained in this larger universe, if you want, of AI. So again, I will concentrate in this context on deep learning, which is again a sub-branch of machine learning and a sub-branch of AI. Okay, so this is just to give an idea that when people tell you that they are doing AI and they only do machine learning, I mean, you have to be a bit careful, because there are things that maybe they are not doing right towards the AI side. Yes.
Sorry, maybe it's a really stupid question, but why logistic regression is at the same level of machine learning? Shouldn't be inside.
Yeah, so this is an example of logistic. So if you want, any function fitting is perceived as as a part of machine learning, and logistic regression is the simplest form of function fitting. Yeah.
Okay.
So if you want, in this sense, the definition that I gave here of being able to approximate high-dimensional functions, it's clear that logistic regression also belongs to that thing.
Okay.
Also, kernel methods that I believe you've been exposed to last week are also part of that.
Noise, for example. In the definition, I see that you don't mention the fact that they could be noisy, no?
Yeah, sure. I mean, that's yes. So I will go into these details soon. But let's say to a large extent, you want to approximate high-dimensional functions. Then the fact that they are noisy will enter the game later on. Yes. Okay, good. Now, what high-dimensional functions? So this is maybe the question that is relevant. Well, essentially, there are many practical problems that you can formulate in terms of finding high-dimensional functions that solve your problem. Okay, So imagine that, for example, your problem is to doing optical character recognition. So which means that I give you an image of a character, let's say a handwritten digit, and I want you to convert this number that has been written, so the image of this number, if you want, into a digital, if you want, version of that number, right? So this is extremely useful, for example, when you, in general, when you do, for example, when you have an envelope with an address that you have written by hand and you want to scan this address and put it, digitalize it on your, in a database, for example, of addresses. So this operation, for example, in this operation, you are after a function that takes the bits of information that are in your image, zeros and ones, and translates it. So if you want, it outputs a number, if you want, that corresponds to that image, right? So this is, for example, one task. There are many other tasks that can be formulated in terms of, again, approximated high-dimensional functions. For example, language translation. So here you are after function f that takes x, an x, which is the a string of text that you can encode in some way as a, you know, as a high-dimensional variable, and then spits out for every x that you give as an input a y, f of x, which is the translation of that language of that string of text in another language. Okay, so you see that this is a problem where the function you are trying to represent is very complicated in general, because it contains all the structure of a given language and of the target language. But in principle, you can formulate all these tasks in terms of learning, as we say, high-dimensional functions. And again, there are many other examples, so driving, game playing, so all of these can be written or thought of as tasks where you have to learn very high-dimensional functions. Why high-dimensional? Because the inputs that you have here, for example, would be all the bits that you have here of information that might correspond to all the essentially all the zeros and ones that you have in this image, or there it can be all the possible string that you can provide of given length to, for example, to that function that you have to translate. So it's clear that these are very high-dimensional functions. Now, so all of these, quite amazingly, has seen a dramatic progress, I would say, in the last decade, and and we are seeing also most of these in the past years. And as we speak, there are more and more developments in this field. But essentially, especially last decade, I would say, has been quite dramatic in the development of this field, because we have seen, starting from 2012, I would say, a huge developments in the field that have started, for example, with deep learning methods that are able to learn functions, again, for example, to do speech recognition, and they beat all the other image classification methods or all the other speech recognition method already in 2012. But this, of course, has progressed a lot, and you've seen, for example, a lot of improvements in the way Google Translate or these kind of tools work. And these are all driven by deep learning. And already in 2016, we were at the point where these kind of tools were better or at the same level of human translators, for example. And more recently, relatively more recently, for example, in 2016, for the first time, essentially, a deep learning approach that was designed by Google DeepMind, a branch of Google, was able to devise a strategy to essentially beat the best human at the game of Go, which again is a highly complicated game, much more complicated than chess. And there the goal was to learn a function that, given a position of your stones on the board, will give you the optimal strategy, so the optimal move in order to maximize the probability of winning your game. So this was the first time that this was done in a way that you could beat the best, if you want, the top professional player in the field. Then there have been many other, if you want, developments that I will not highlight. So today I will just cover the basics. So one thing that, for example, you might wonder why this happened has happened now, or if you want, in the past decade. There are many reasons or many possible explanations. So one is that there's been an increase in dataset sizes. So if you want, as I will show you later on, these functions are learned using a large amount of data, and the availability of this large amount of data has happened, consistently only recently. So, for example, you can see that the dataset size, so the number of examples, for example, that you have in this kind of datasets, has increased exponentially with time, and this coincides also in a sense with this exponential increase in the usefulness of deep learning. So this is one possible explanation. The other one, so this availability and the possibility to store data as well with larger hard drives, for example. And the other one, which is also very important, is that we are able to use specialized hardware, for example, GPUs and TPUs, that are essentially dedicated to deep learning and other kind of tasks that are necessary to realize this, to approximate these high-dimensional functions, as I will tell you in a second. And these developments have happened really recently, thanks to development of specialized hardware such as GPUs and TPUs. And another reason, I guess, is that the kind of models, the kind of, if you want, parameters that we can fit in these functions that we are trying to represent, and I will tell you in detail what these functions are, but think of these functions as an ensemble of neurons for the moment. Well, the number of parameters of nodes that we can put in these functions, these neural networks, has also increased exponentially with time. And we are at a point in time where, I mean, it's been somehow forecasted that around 2015 or 2050, we will have a number of neurons in these objects that is comparable to what we have in humans. Of course, it doesn't mean that they will reach human intelligence by 2015, but this is an indication that at least these models are becoming more and more complex. You know, this, again, there is a slight correlation, if you want, between the kind of intelligence that you can achieve with these functions and the number of connections or the number of neurons that you have in this, and the kind of corresponding living beings that have the same amount of neurons. Of course, this is from the biological point of view, it's a bit delicate, but I mean, let's say this is one argument that is often brought to understand or to just justify why there's been such a huge development in the last years. Okay, good. So now, I mean, after this quick and dirty introduction, I will move into some more technical details. So I think it's a good time to switch the presentation and move to the. So as I was mentioning before, the main idea of these approaches is to learn, is to represent high-dimensional function. So in this sense, the machine. So in this machine learning, if you want, approach, is nothing but, if you want, the terminology to indicate these are high-dimensional functions that we would like. Okay, so I can use the blue maybe, I mean, later on. But okay, so here it's written the machine, so I hope that this is clear. So what is this high-dimensional? So let me just define it. So now I have some high-dimensional function that again might be the function that takes an image and returns the corresponding digit, for example, in those kind of problems, in image recognition problems. So I have a function of n variables, okay? So x to xn, I will call this vector x. And the way we parameterize typically these functions, at least in deep learning, is through what we call a multi-layer perceptron, okay? So that's at least the simplest way of doing so. So the idea of a multi-layer perceptron is quite simple. So you have if you want, a combination of linear and nonlinear transformations. So let me write it down and then I will explain. So I have some weights, and then I have some function phi2. Then I have w phi1. Okay, great. So the way you read this object is from the right to the left. So you see that x now is the input, if you want, to my function. Essentially, so what we do is that we take, so these w's now are matrices, okay? So these are just matrices, for example, of real numbers. that we in jargon are called, for example, weights. Oh, I guess I have to use this. No, it's okay. So these are called the weights of the neural network in jargon. Okay. So what we do, I mean, and also I will, we typically introduce some a vector or what we call, so these are vectors. So that this BI that I will tell you in a moment how they act. So these are vectors and are called the biases. Okay, so what does it mean? So what does this writing mean? It's very simple. So for example, if you take this, so it means that we are doing essentially an affine transformation of my input. So for example, so when I consider the product, if you want, of this W by X, so actually what I'm meaning more if you want, more precisely is that I'm taking my W's, so my matrices, let's say W1, for example. I'm taking a linear combination with the vector that is on the right. Okay, so I'm applying this matrix on this, and then I'm adding a bias, so-called bias vector. Okay, and I will call this intermediate object Zj of L. For in this case, Zj of 1. Okay, so this is just another. So if you want, I'm using this definition here as which is not strictly a linear product, but it's an affine transformation, where I apply this matrix plus some shift that we call the bias term to my vector of inputs, and then I get out of this another vector of outputs. Okay? And then what I do is that I apply to all the components of this vector z a nonlinear transformation phi. Okay, so phi L of x, if you want, is a one-dimensional function, if you want. And typically, this is a nonlinear function for reason that I will explain in a second, or at least for motivation that I will explain in a second. So, which means that at the end of this operation, for example, so after I apply this affine transformation and I get a vector, then I apply to all the components of this vector this nonlinear function. So I will get a vector of numbers that I will call in this case aj1. Okay, so what is aj1? Is nothing but, again, the action of applying this one-dimensional function to all the components of this affine transformation. Okay. So here I have now another vector. I apply again another affine transformation with typically different weights, different biases, then another nonlinearity, and then until I reach the final layer, so-called, of this transformation. That is called, in this case, L. Okay, so I do this operation L times. And as you can see, so quite crucially, the dimensionality of the output is defined by the dimensionality of the last, if you want, layer. So in other words, by the size, if you want, of this matrix on the last layer. So if you want, by the inner dimensionality J, which is a free parameter. And for example, if I want a scalar function, the last W will have only one J, if you want, one single output. Instead, if I want a vector function with a vector output, then in this case, the last dimensionality can be more than one, and it can be arbitrarily, can be chosen by essentially by. Now, what I want to do is that I want to give you a visualization of this in terms of a network representation. So if you want, I can also introduce. So is this clear? I mean, is it yeah, too trivial or too? Yeah. Yes.
Just that is not clear. When you apply the affine transformation, wouldn't it be sum over j and then the surviving index will be the ith index? It's just that it's a bit weird to fix the component of the x vector and then just sum over the columns of the weights. You understand? Like just
sorry. Yeah, of course.
sum over j and then
Sorry. This is wrong. Yeah.
Okay,
this is
yeah,
sum over I. Yeah, of course. Yeah.
Thank you.
Thank you for the for being. Yeah. Thank you. Okay, good. Yeah, indeed. So J there is the inner dimension, which is free, and it's what. So, but now, yeah, indeed, I guess all these things are a bit clear, at least for some of you. I guess if you use a graphical notation. So typically, the way people visualize these functions, again, which are called multi-layer perceptrons, is in this way. So you visualize, so you put your, if you want, your input vector on the left. And you imagine that these are all the components. So these nodes are the components of your input. Okay. So imagine that now these are my input, the components of my input vector X. I draw them as little nodes. Okay. And then, so typically, what you can do is that you can, for example, you can represent these intermediate layers of transformations also as nodes. Okay, so for example, you can think that this node here would correspond to the first transformed A. So for example, this A1, 1. This other node would correspond to A2, 1. Okay, until you reach, I mean, with some other connections, you will reach the last A. I called it this C1, 1. Okay, so if you want, in this graphical notation, the connections or the edges between these nodes just correspond to the non-zero value of the weights somehow that connect, in a sense, your inputs to these A's. Okay, so for example, if some of those weights were 0 and you didn't have any weight between, I don't know, this X and this one, then you would not draw an edge there, and you would just have a corresponding diagram without those edges. Okay. And you see that here I've defined this intermediate dimensionality as a C1. Okay, and this is the if you want, this is what we refer as the width of the neural network. So this inner index J, so the number of possible values that J can take, is called in jargon the width of the neural network. Okay, and it's something that you can fix, and it's arbitrarily chosen, and it's part of the choice of the architecture that you're doing. And again, then, I mean, you can do this game many other times, for all the layers that you have, and you will have other intermediate layers until you reach the last, if you want, final layer. So let me call this, for example, AL1. So imagine that, for example, you were interested in representing the scalar function, so with only one output. So in this case, you would have that the width, if you want, of your last layer would be 1, and you would have only one neuron in the output. Okay, so in this case, for example, you would have that A1 of L corresponds to your F of X. Okay, so again, just to be clear, so I defined this CIL to be the width of the multi-layer perceptron, MLP, or the deep network if you want. So this is, for example, C1 would be the first width, and L in jargon. So the number of layers that I have is called the depth of the neural network. So the depth of the neural network or of the multi-layer perceptron. Okay. I guess that you are already familiar with this, but it's just to somehow clarify the notation that I will use in the. Good. So now that we have this notation and we have these definitions, if you want, I guess it's useful to understand why we are using exactly this kind of representation for these high-dimensional functions, why they make sense in a sense, right? So why don't we use a cosine or a sine? I don't know. Okay. Why don't we use a Fourier series or whatever? So why this form? So there are many reasons. All of them are, if you want, to a large extent, empirical reasons. So if you want, it's not highly justified. There are not, there are some theorems that I will discuss, but in many cases, these are justified by the fact that these forms work well in practice for applications. But let's say, so the first reason, I guess, why these kind of architectures or this kind of representations were introduced was mostly biological. So if you want biological inspiration. Because essentially the idea is that you can think that these nodes are a mathematical, so highly idealized representation of how a neuron works. So essentially what we know from the biology of neurons is that we know that if you send some so if this is essentially the electric signal that enters into a neuron, then a neuron will start spiking, as we say. So it will start emitting, if you want, another electric signal, depending on the amount of incoming signal. So if this signal is smaller than a certain threshold, then the electron will not emit an output, and it will stay zero, at zero level. But if the incoming signal is larger than a certain threshold, then it will start spiking, as we say. So we'll start emitting an electric signal that can be routed to other electrons that are in your neurons network. So you can think that essentially what happens in an actual neuron is that you have a lot of incoming connections that come from other parts of the brain. And if the sum of these incoming electric signals is larger than a certain threshold, then the outgoing, the output of these neurons will be finite. Otherwise, if you don't have enough, if you want stimuli on your neuron, then this will not spike, this will not emit an output signal. Okay, and this kind of phenomenology, if you want, this kind of idea is, again, the inspiration for the forms that we use here, because, for example, you can, so for example, if now we idealize my neurons and I see them as something that is connected to this layer of other neurons that are somehow below them, you can think that these weights represent the amount of electric signal that is coming into this neuron here. And A, so the application of this nonlinearity, is a way to model this spiking effect. So for example, if you take a phi, which is 0 for x that is smaller than 0, and linear, for example, or something that activates after for larger values of x, then you get a similar phenomenology that you have in the brain. Okay, so this is the biological intuition. Again, if you speak with people actually working with neurons, they will tell you that this is a terrible justification and it's not really rooted into the reality. But at least, I mean, that's one of the reasons why people introduce these models, and that's why they're called neural networks and not something else. Okay, so this is the first justification. To me, it's not certainly not the most important, but it's certainly convenient to tell about this. Now there is a second justification which I think is a bit more interesting. and it's more mathematical. So in this, I will be particularly careful because, as you've seen already, I guess I'm not particularly formal. But the mathematical reason, at least the way I understand it, if I take the blue again, so the mathematical reason, so this is reason number 2, if you want, that was reason number 1. So the mathematical reason. Well, it can be traced back to actually Kolmogorov and Arnold, so two great and the reason is given by a famous representation theorem proven by them already in the 50s. And the theorem, so again, informally, if you want, you can look up the details, but it tells you that if you have a high-dimensional function f of x1 up to xn, you can always represent it as a combination of two essentially one-dimensional functions. So let me write down the final, if you want, form, and then I will comment. So you have a capital phi, and then you have a sum over p that goes from 1 to n, lambda p small phi of xp plus eta, I don't know, q plus q. Okay, so the details are okay, so what are these capital phi and the small phi? So these are two. So phi of x, if you want, and the small phi of x. So these are two one-dimensional functions. Okay. And actually, you can take the small f phi, so phi of x, this one, the inner functions, to be bounded between 0 and 1, so real function bounded between 0 and 1, and to be actually independent on the function f that you are trying to represent. In a sense, then, this small phi is a universal function that can be used to represent any arbitrary large f function. So the only function that now will depend on the details, if you want, of the f that you're trying to represent is this capital phi, which is still, however, 1D function. Okay. So I don't know if you realize the, yes.
What class of functions are we trying to approximate? So it's
yes. Okay. So okay. So I think the statement is true for continuous functions. Yes. No, not the derivative does not need to be continuous, just continuous. Yeah. And these are scalar functions. I'm not considering the vector case, but okay. I mean, when you have, but it's similarly, you can similarly do it. So the beauty of this, as you can understand immediately, is that in principle, you can represent this high-dimensional complicated at-will function using only, if you want, combinations of linear combinations and applications of nonlinear functions in this form. Okay, so and you see that this is reminiscent of the neural network form that we've seen before, because you have, in essence, you can think of this as the first layer where you apply these transformations, and this as of a second layer, which is the second nonlinearity in your neural net. Yes.
Sorry, what's the variable eta? Like the
Yes. Okay, so eta is a real number. that is fixed by this representation. I mean, you can must be found in each. Yeah. Q is an integer. I mean, and the P is an integer that runs on the dimensionality of your. Yeah.
With that structure, wouldn't it be possible to, for example, choose phi as, I don't know, just leaving XP, you know, just maps XP plus NQ to XP, and then the big phi will be just, for example, a polynomial. So I mean, couldn't you express the same with the same structure, a polynomial or a Fourier series expansion? I mean, why is it particular? I mean, I see the structure there of the neural network, of course, but
no. So
would it be like also?
So the beauty of this is that, for example, if you add a representation of this f in another discrete basis, let's say in a Fourier basis, you need to specify exponentially many coefficients, essentially in n, right? Because you have imagine that you have a grid, I don't know, or a simple basis, then the number of coefficients that you need to express that function is exponential in n, right? Instead, here, in principle, I do only polynomial operations in representing the function. In principle, there's a catch that I will tell you in a second. Okay.
Yeah.
In a second. So but this is a motivation to the fact that if I use now a non-linear representation of my high-dimensional function, at least in principle, I can find a compact representation, where compact means that I run only a polynomial number of computations if I know how to compute phi and large phi. Right. So instead, this statement is not true in general. For example, if I pick a basis like a Fourier basis or any other basis of polynomials, because there, in general, at least in principle, I need to run. I need to compute all the expansion coefficients and then sum all of them to find f of x. Okay. So this is the main conceptual motivation beyond using non-linearities instead of linear representations.
Do they also give some kind of recipe in order to find phi?
Yes, yes. So there are many papers that are a follow-up of this by now I don't remember the name. I think it's Pecken, but I'm not sure. So I can give you the references later. So I wanted to keep this informal, but I understand that being mathematician, this was not the best way to enter the game. But yes. So essentially, if you can compute f, then there are strategies to compute phi's. But what is the problem? Okay, so let me give you. So this would completely kill the course of dimensionality if true, but there's a problem. So the problem of this is that in general, representing this phi will need an amount of bits of information which will grow exponentially, typically with n. Okay, so if you want, these are still one-dimensional functions, but these are one-dimensional functions that contain, if you want, the value of your function f, large f. So if you want, the problem is that if you try to represent now these smaller phi, these one-dimensional functions, f and capital phi, with, I don't know, linear combinations of polynomials, because at the end, these are one-dimensional functions, so in principle, they're much easier to approximate, then you will need to have a precision in the expansion coefficients that you're using in your basis of polynomials that is essentially exponential. So this will kill you in practice in the applications that you try to do. Okay? So, but still, this theorem is interesting because they are the mathematical basis. And again, hopefully somebody more rigorous than me will tell you about this later on. But I just want to point you to the I mean, at least to the name of the theorems, to what we call the universal approximation theorems. So in practice, so since these phi and are hard to compute because they require high precision, what you can do is that instead we fix some nonlinear function, for example, I can take phi of x to be, I don't know, the hyperbolic tangent, so, you know, some functions that I know how to compute, okay? Or could be, I don't know, cosh. I mean, there are many choices. Okay, so some hyperbolic functions, for example, are typically used in this context. So now if I fix the nonlinear functions, okay, then this statement is not true anymore, in the sense that I cannot find in general a compact representation of an arbitrary f of x. But, and this is a theorem that was proven by Sibenko in the 80s. Now, if I relax this constraint, then you can show, okay, that so essentially the multi-layer perceptron form, which is the case where I don't fix these phi's, but I take some phi that I can compute. So in this case, then I can represent so any, if you want, a continuous valued f of x, but so essentially the width of the second, so I can still represent it in this form, which is a depth 2, if you want, a neural network. So I can still represent any f of x with a multi-layer perceptron of depth 2. But the inner dimensions here that here are polynomial can be in general exponential, are in general exponential. Okay, so if you want the first, so if you want C1, so the C1, so how did I call it? Let me see. Yeah, C1, so C1, no, C1 was the dimension of the first layer. So C1 is in general of the order of the exponential of n. Okay, so I'm giving a very informal description of this theorem. If you want, you can have a look at the details. But essentially, the idea is that if I relax now the fact that I'm not using the exact, if you want, functions that are prescribed by Kolmogorov and Aldo, but that in general are hard to store, if you want, and compute for a given input, and I use instead a function that I can work with, then in this case, if you want, this inner summation here, essentially, will need to run over a dimensionality which is exponential. Okay, so this is the true problem and where you recover the course of dimensionality. But still, to me, this is interesting because it tells you that, at least in principle, these nonlinear transformations can be more powerful than linear ones. So that's a justification, at least, for using nonlinear transformation instead of using a simple expansion into a sum basis of polynomials. Okay, so that's one of the reasons, at least that I see to be one of the main advantages of working with nonlinear representations of functions. There are many other representation theorems that have been shown. So, for example, there are follow-ups, if you want, in this field that can be interesting, especially for you, but that I will not discuss today. So, for example, it has been shown that if I fix the width of the neural network, but I grow the depth, I can also be universal. So I can describe any continuous function, provided that now in the worst case scenario, I will grow the depth exponentially now with the input sides. Okay, so here instead, what we are doing is that we are fixing the depth to be 2, but we are growing potentially in an exponential way the width of the first layer. Okay, so there are these two ways of growing exponentially these neural networks that are essentially equivalent. But there are other state theorems more recent where they prove this other statement for the depth instead of the width, if you fix the width and not grow the depth. Okay, I can give you some pointers to these references later if you want to learn more about this. Okay, good, great. So these are some of the things that I wanted to tell you a bit more on the justification of this form. And now I want to dive into the applications. So the applications that we can do with these multi-layer perceptions. So the first one, I mean, at least the one that is conceptually easier to understand, it's what we call supervised learning. Okay, So supervised learning is a kind of framework, if you want, in which we try to represent this function, so to find approximations for these unknown high-dimensional functions by using data. Okay, so what does it mean that we use data? So for example, imagine that I have again the task of taking images of handwritten digits and classifying them as being 1, 2, 3, 4, or 10. Okay, so you can imagine that now the input, if you want, I have a vector of inputs, and one now indicates the fact that this is the first, if you want, element in my data set. So I have the first vector, if you want, of inputs that would correspond to some digitalization of my image. Okay, so for example, imagine that somebody takes an image of an object, for example, in this case of a number, and written number, then I can always convert this number in some digital form where a black becomes a 0 or a white becomes a 1 and vice versa. Okay, so you can think that I can represent an image always as a vector of zeros and ones. Okay, and now the dimensionality, if you want, of this input vector will be the number of pixels that essentially I have in my image. Okay. Great, so now you can imagine that in this data set, I have a lot of different images. So again, a lot of different vector of zeros and ones that correspond to different numbers. So for example, this might be the image of the handwritten digit 3. The input that corresponds to this handwritten digit 3, or I might have another element in this data set, which is another image that corresponds to, I don't know, the hand digit written 1, okay? And that corresponds now to a different set of zeros and ones. Okay, because this we'll have less whites here, more black there's, and all sorts of different. Okay, and now I can, so in this supervised learning setting, I assume that somebody has done the following for me. It has pre-classified these input images into the output that we would expect a machine to output when given this image. So for example, I might expect that in this set of images that correspond to my data set, I have some, if you want, variable y1 that corresponds to the expected output of this classification approach. So for example, in this case, the string 3. Okay, or in this other case, y2 might be the string 1. Okay, the string, or you can think that this is truly like the number, like the real number 1 or 3, okay, or the integer 1 or 3. Okay, so and I have in general many of these cases of pre-classified images where somebody given an image has also already taken the care of writing down this is a 3, this is a 1 for me. This is what people have done actually using high school students in the famous MNIST dataset. So they decided in Canada, I believe, to pick 1,000 students from high school. They gave them images of handwritten digits and they asked them to classify them by hand. And this was used to form this famous dataset of images that then is used to train machines. Okay, so you always need in this context of supervised learning some manual input from humans, if you want. That's why it's called supervised, because the humans are helping the machine to then learn this high-dimensional function. Because indeed now the goal would be to find, if you want, some. So the goal would be to find some high-dimensional function f. So some representation of an high-dimensional function that given, for example, one of these, in general, given one of these input vectors that correspond to a given image, so let's say xi, okay, spits something that is as close as possible to the expected prediction yi. Okay? And in general, we want to find, if you want, a parametric function that will depend on a lot of parameters that I will call here P. So this P can be the ensemble of the weights, the biases, everything you have in your neural network, okay? So in other words, we are representing now this f of x given P, my parameters, with a neural network, and I want that at least on the amount of data that somebody, the high school students have pre-classified, I match their predictions. And then the hope is that this will be able to then generalize to some unseen amount of data, so unseen, if you want, images, because it has learned by using these, pre-classified images how a 3 looks like, or how a 1 look like, or a 10 or a 2. Okay, so this is the intrinsic idea of supervised learning. So, but this is, relatively easy to do. Well, I mean, at least conceptually, because then what we are after is really, a simple fitting, if you want, procedure, where we define what we call a loss function, L, that will depend in general on all the parameters that I have in my neural network, P that goes from 1 to NP. NP now is the number of parameters. And I can define this loss function. Again, this is, this field is full of jargon, but I mean, that's what we call the loss function. Right, sorry for your loss. Okay, anyways. So you can write this as, so for example, one possible definition of this loss function is if you want, the L2 difference between the predictions and the actual value that we expect. So for example, I can define this as the L2 loss, so-called. So it will be the difference between my prediction minus my yi. And I can take, for example, again, an L2 loss, which means that here I put, I have a square, but I could take also L1 or any other norm that you like. But let's say in the simplest case, I can just take the L2 loss. And you can see that this loss function will be 0 for a set of parameters that are in my neural network, only when my neural network exactly matches for all the points, NS, all the data sets points, all data set points that I have, the predictions that my students have written down for me. Okay? So now the goal is to minimize this loss, right? So that's why it's called the loss, because we want to minimize and reduce the loss as much as possible. So the idea, if you want, the learning process, so-called learning, is essentially jargon for minimizing, in this context, the loss function. So I want to, if you want, the picture is that I will have now some complicated high-dimensional loss function that will depend on my parameters P. Okay, and in principle, I want to find some, ideally the global minimum, or I mean, I will discuss this in a second, but let's say in principle, you want to find some values of the parameters that I will call P star, that are the optimal parameters, if you want, that correspond to the set of parameters that minimizes the loss. Okay, so I will discuss in a second if we really want a global minimum, a local minimum, but let's say in general, learning means that I want to minimize this loss. Okay, good. So what can we do then? I mean, yeah, we can do many things, and I guess that last week you already saw some of these, optimization approaches, and you are fully aware of how to optimize a high-dimensional function. But I want to give you a perspective to this learning problem, which is maybe slightly different. Because as Alessandro was mentioning, there is noise. So, okay, so we have to see where the noise is, okay? Because until now, there's no noise whatsoever. So where is the noise and why the noise is good? Okay, so in general, so the simplest thing that you can do when you want to minimize a function is to do gradient descent, right? So gradient descent, I mean, again, you've seen this in detail, so I will not go into the I mean, I will just rewrite down to fix the convention, but essentially it's an iterative approach where at step k+1 my parameters p are updated using my the old values at step k. So this k now, if you want, is an index of this. If you want, this is the step of this iterative approach, right? So you start with some initial guess of your parameters, and then you update them in this way, and then you update in this following the direction of the gradient, which will be now, for example, the gradient of p of my of my loss function at L of p. Okay, and this small, typically small factor eta that we put in front of the gradient is called in jargon again the learning rate. I'm doing an effort, guys, so I hope you appreciate it. Okay, anyways, good. So what is the problem in general of the gradient descent? I mean, or a feature of gradient descent. A feature of the gradient descent is that this will typically converge to any local minimum, right? So for example, if you start your procedure with a set of parameters that are here in the loss function, let's say this is my P0, okay? And then you follow the gradient and data is not too large, then you will end up in the first local minimum that is, if you want, topologically closer to your initial point, okay? So there's no way you can find, for example, the global minimum using all the gradient descent or any other local optimization approach, even with Newton, okay? So this might be a problem because typically, actually, these loss functions are highly complicated, non-convex things that you can have depending on nonlinear functions and all of that. So finding the minimum or finding a local minimum might not be the best thing to generalize, for example, this function to unseen data sets. Okay, so then then what is the noise and how can it help us? Well, this is the idea of stochastic gradient descent. Or in jargon, I mean, also the acronym is SGD. Okay. So what do we do in SGD? Well, in SGD, so let's first write down the gradient in the standard gradient descent formula. So let me call this GGD. Okay, sorry for the slight. So this GGD, so the gradient of the loss function in the standard formulation, if you want. So this is by definition, if you want, the gradient with respect to my parameters of the loss function P. But I wrote the loss function over there. It's still written over there. So you can immediately see that I can write this as 1 over the number of samples or number of examples that I have in my data set because of the linearity, if you want, of the gradient, right? So I can write this, let's go from 1 to ns. And then I have the gradient with respect to my P of this f of xi of P, given P, minus yi squared. Okay? But now you see that I can write the full gradient of this loss function as a sum of gradients, each one taken over, I mean, essentially each one depending only on the ith example in my dataset. Okay, so if you want, I can take this, I can rewrite this as 1 over ns, sum for I that goes from 1 to the number of examples, ns of some g that I will not write down explicitly, but that you can easily compute. This is a quadratic function. I mean, at least implicitly in terms of the gradients of f, of xi and p. Okay, so if you want, I will now call this g. So this is what we can call the per sample, per example gradient, or per sample or per example. Okay, it's fine. Gradient.
Sorry, just a question. So it depends also on yi, or you mean that xi is both? Okay.
Yeah, this will depend also on yi. Yeah, if you want, we can also put this more explicitly. Yes, yeah. So, but the only thing that I wanted to make, the only point that I want to make here is that this does not depend on all the other points, of course, but only on the given point xi, yi. Okay, and it's a universal function in a sense, right? Okay, good. So, so the main, if you want, insight of this stochastic descent is that we now approximate, if you want, this summation here. So with a much smaller number of samples than the original one. So I will just use now these MB samples, which are typically taken to be much smaller than the initial number of samples or examples that I have in my data set. There could be millions or billions of examples. But I approximate this gradient by subsampling, for example, only a subset of examples that I have in my initial data set. And this MB, this B, so I call this B because this is called in jargon the batch size. Okay. So MB will be, I can call this as the, if you want, the batch, or yeah, batch of examples. So, and what am I doing? Well, I didn't write it down, but I discussed it already. So essentially, I'm approximating this. So I'm defining, if you want, the gradient descent as some subsampling of the original data set, where I compute now this G function, so this per example gradient, only on some subset. Yeah, and this depends also on yi, of course, sorry, of my data set. Okay, so if you want, instead of running the full summation on the old data set, I just pick some randomly, for example, uniformly, some subset, and I compute the gradient over those in this way. Okay, so why this is noisy? Well, you can see already where we're going, maybe. Because right. So because okay, so because in the limit, so let me go to the other. So is it clear, at least operation from the operational point of view, what you are doing? Yeah. Okay. Okay, so the idea is that, so what is the noise? Also, what noise, if you want. So the idea is that the, now imagine that the number of samples ns is so big okay, that I can think. So if ns in a sense goes to infinity, so if my data set is very large, then you can think that the original definition that I wrote there, so if you want G of, yeah, unfortunately I can't really do this, but okay, I hope you can still see. So G of GD, so my original gradient, computed with a number of sample ns, right, that goes to infinity. So let's say, okay, so let's say in the number in which I take this number of samples going to infinity, so let me indicate this, like this. So I can interpret, if you want, that summation, the first one that I wrote on top there, okay, as the statistical estimate, so the expected value, if you want. So let me write this like this. So the expected value for x that is drawn from some unknown probability distribution P of x of this gradient per example gradient function G of x. Okay, so if you want, this is the definition would be this is the sum over x over all possible values of this variable x, P of x, G of x, and P. Okay, yeah, there's also y, but I'm just for the moment forgetting about it. And you see that essentially what we are doing when we take a finite ns is that we are approximating this expected value with a finite sum, if you want, over the sample, over the data set. So we are approximating this now with 1 over ns sum over from I that goes from 1 to ns of G of xi and P. Well, now I'm assuming that if you want, with my xi drawn from P of x. So if you want, pi of x is the unknown probability distribution for the data set. Okay, so you can think that there is some pi of x that is the probability distribution of all the images that are all the handwritten images. Okay. So, and you can see that effectively, if ns is large, we are approximating this formal expected value with a sum over samples that are distributed from that. Okay. So, but this means that we can use, for example, the so if you want, if you estimate this expected value with a finite sum, you know that this will be distributed according to a Gauss, so according to a normal distribution with an error that will scale like 1 over the square root of the number of samples, right? So this is the error on the mean that you get when you approximate an expected value with a finite number of samples. Okay, so let's say I can write, if you want, my G, my gradient G as GD, computed with a finite number of samples, and S as the GD, if you want, so the infinite one, plus some normal with some sigma that is this is a bit informal again, but so some normal that is 1 over this goes like 1 over the square root of the number of so this is MB because I'm approximating this with the batch right now. Okay, like 1 over the square root of B, MB. Okay, so you see that if I send now MB to infinity, so here I'm effectively considering, and now I'm taking that NS is infinity for all purposes, and MB is a finite number of samples that I can take from this universe of examples. And what I'm telling you is that if I draw uniformly, for example, from this set of possible x that come from pi of x, and I take MB of them, then the gradient that I estimate in this way will have a mean, which is the exact, if you want, value of the mean when I take MB going to infinity. Sorry again, but then I will have some, corrections on that whose variance will scale like 1 over the square root of b, f MB. Okay. So you see that there is some noise in this plot. In this sense, there's noise because I don't have the exact estimate of the gradient, but I have only an estimate which is exact in the case when I take MB goes to infinity, but I don't want to do that in general. So what is then the SGD approach? The SGD approach is the idea of doing exactly this update, but with the SGD gradient. Okay, and now this is the stochastic gradient descent. Okay, so the idea indeed is that instead of taking the exact gradient, now I take a statistical approximation, if you want, of my gradient that has some intrinsic noise. Okay, but still the form, if you want, of the update that I have in my equation is exactly the same that we were using in the previous case. So but what I can do is that I can expand, in a sense, this equation. Okay, right. So noticing, so using, if you want, that equation that I wrote up there, very informally. So I can write the G, so the exact gradient, if you want here, I can put the exact gradient, GD, which would correspond to taking infinite number of NS. And then I have this correction, which is a normal distribution. Okay. So here I'm doing an important approximation that all the components of this, if you want, of this gradient have the same Gaussian distribution and they are uncorrelated. So in general, this is not true. But just to simplify, I'm assuming that, so this normal, which is itself, if you want, a Gaussian, sorry, a vector. So for each of the components of the gradient, I've assumed that each of the components is given by some mean value plus a Gaussian fluctuation with a sigma that shrinks to 0 like 1 over the square root of NS. So in general, you will need instead to compute the covariance of all these variables. But let's assume for a moment that this is a much, easier way to analyze what I want to tell you from a physics perspective in 1 second. Okay? So, but you see already, at least phenomenologically, what's going to happen here. So we have an update where we have the exact gradient plus some noise that is given by a normal distribution to the first, in this approximation at least. So why do we care about this? Well, because in physics we have something very similar. We have something very similar, which is known as the Langevin equation, so that maybe some of you know about. So this, right, so let me write it down. So typically in physics, you can discretize so when we characterize Brownian motion, which is essentially the motion of particles that are subjected to Newtonian forces, so essentially all classical mechanics plus some temperature, so the effect of some temperature. And in this case, so for example, if we discretize the motion of these particles in time, so now I imagine that P are the positions of some particles that I have in a box, okay? And these particles are subjected to, in some small time interval, delta t, to a force which is given by the gradient of some energy, okay? So this is the Newtonian force, right? So this is would be so the gradient of the energy, right? So sorry, let me call this the gradient. So the gradient of the energy with respect to the particle positions. And then I have, so this is why this is not, so without this other term, this would be just Newtonian mechanics. So your particle move under the action of some gradient of the energy. But the additional term, which is non-Newtonian, if you want, it's the one that you have in the Brownian motion, is the fact that you have some normal distribution for your forces, if you want, that is distributed according to and the variance, if you want, of this so if you want, the variance of this Gaussian is proportional, so the square actually, so sigma square will be proportional to the temperature of the system. So this is the temperature. And this is a small time step delta t. So if you want, what happens is that at each time step, my particles move under, so at, let's say a particle at time t, and a particle at time now t plus delta t, okay? Or if you want, I can call this tk and the t of k plus 1, which is also a notation that I'm using at the same time, okay? But the two times differ by a delta t time step. So essentially, not only they are affected by this force, this Newtonian force, but they're also given some random, if you want, force, whose intensity, whose strength is proportional to the, essentially to the square root of delta t times the temperature. So if the temperature is larger, physically what happens is that this force, this random force will be larger. And this is, if you want, the essence of this Brownian motion that was introduced and observed and studied by Einstein also, when you have pollen in the air that, for example, when you can see particles of dust in the air that they move randomly in a room, and the room that is illuminated by light, they see that they do a random motion in the room, and this is exactly this Brownian motion. So you have Newtonian forces plus some random forces that are distributed proportional to the temperature of the system. So why did I write this down? Because it's exactly, I mean, at least in this approximation, similar to what we have in the SGD. And an interesting thing that we know from physics is that asymptotically, so if you run, if you want, this dynamics for a long time and delta t is not too large, we know that these dynamics, so this Langevin dynamics, will find a steady state in which this particle position that I'm also calling P will be distributed according to the Boltzmann distribution. Okay, so this will be distributing according to the exponential of minus E, so the energy of my system divided by the temperature, divided by some partition function, some normalization Z. Okay, so this is known as the Boltzmann weight. I mean, I'm sure that all of you. Okay, so if I run now, if I observe on average where my particles will be, they will be distributing according to Boltzmann. So the larger the energy, the temperature, so the more excited they will be around, they will float around in the room. If T instead is small, they will just go into the ground state, if you're in the lowest energy state of the system. So this is an analysis that can be made rigorous. I'm not doing it, but I mean, you can find in all books. But now, again, this is, I mean, at least in a first approximation, what happens also with gradient descent, with stochastic gradient descent. Because if you look now at that equation that we wrote down on the left, this is formally at least similar to what we wrote on the right, what I wrote on the right for the Langevin. We just have to do a few change of variables if you want, that I will do for you. And the change of variables, if you want, is that now I'm mapping. So unfortunately, I called the PIB in both cases, so that should have been ours. But okay. So let me do it because. So as I was telling you, so these are particle positions, right? So let's call them R. So it's clear that I'm talking about particle positions and not something else. Okay. So if you want, so the connection that, I mean, I already anticipated by doing this mistake was that I'm mapping, if you want, parameters onto particle positions. Okay? So if you want, in this framework, I have as many particles as many parameters I have in the original framework. And I'm also mapping the learning rate onto the time step delta t. Okay, so you see that I have eta that multiplies the GD term, which was just the gradient of something, and there I have a delta t that multiplies the gradient of something. And indeed, what I'm doing is that I'm associating, if you want, the loss function that depends here on p to the energy of the system. So this is the crucial, if you want, step, because I'm saying that the energy there is associated to the loss function here. Maybe it's useful to rewrite this, but so here I had the minus eta, the gradient of the loss function of p, right? So you see that also essentially the loss has the same role of the energy there. And then in this small dictionary, then I also have that sigma squared, if you want, that there is equal to 2t over delta t. But 2t times delta t, sorry. Okay, so this means that now I can, by using this analogy, I can claim, if you want, at least in this simple case when I'm assuming that my parameters are independently distributed, that the target distribution for the SGD will be also a Boltzmann distribution, the exponential of minus the loss function now that plays the role of the energy over some effective temperature that I will call T SGD. Okay, and you see by essentially by doing this this connection and remembering that sigma square in this case was given by, so sigma square was given by essentially something that is proportional to, so let's say sigma 0 squared divided by MB, the batch size. So you see that now I can connect, if you want, the temperature to the batch size and the learning rate. So this TSGD, if you do all this substitution carefully, so will be something that is delta T sigma squared. So, okay, so I mean, at the end, you will find that this is eta, so the learning rate over something that is proportional to learning rate over the batch size. So if you want, in this framework, the interpretation is that when the batch size goes to infinity, your temperature goes to 0. And what you are doing is that you are essentially doing Newtonian dynamics without any noise because you are quenching the system to the ground state directly. But there is also another mechanism according to which you can change the temperature, which is by reducing eta, so the learning rate. Okay, and indeed, this is exactly what people do when they use more advanced approaches that go beyond SGD. For example, in Max, I don't know if you introduced this a bit last week. So these are adaptive stochastic descents in where typically, according to some schedule that can be understood more or less empirically, you typically anneal, so you change these etas and you make them smaller and smaller while you do your optimization. So, and then the physical, if you want, image of this is that, for example, if I have a schedule in which the learning rate at step k plus 1 is smaller than the learning rate at step k, this corresponds in a sense to lowering, I mean, in this exactly in this sense, because eta is directly proportional to the temperature, corresponds to lowering the effective temperature of the system. So and so you can, so then this means that if I have now my loss landscape, if at the beginning I start with a large eta, for example, I will have more fluctuations due to this effective large temperature. But then while I proceed my optimization, I am cooling down the system, and I have chances to find the global minimum rather than the local minimum. So if you want the effect of the noise, if you combine it with a schedule that, if you want, makes eta smaller and smaller, is equivalent, again, in this simplified picture, to doing a simulated annealing. I don't know how many of you are familiar with this. But simulated annealing is essentially one of the most powerful techniques inspired by physics, not by chance, that is used to optimize high-dimensional functions. Okay, so the idea is that you start from your parameter distributed with some high-dimensional, with some high temperature T, and then you anneal, so you lower the temperature little by little until you find the minimum of your function. And in this context, this simulated annealing is done for free, essentially, provided that you use a small batch size, so not infinity, otherwise you wouldn't have any noise, and T would be 0, and that you anneal, so you reduce T sufficiently while doing your optimization. Okay? How much time do I left? 0, right? Yeah. I think I should, yeah. Yeah, okay. So, yeah. So I think I will just, okay. So I will conclude here saying that the only ingredient that is remaining, if you want, that I haven't discussed yet, which is pretty important if you want to implementing, if you want, this approach, is how do I compute the gradients of this loss, right? So for example, how do I compute these G functions that I wrote before? So given the form of my multi-layer perceptron, specific form and the explicit form that I wrote before, how do I compute the gradients? Okay, this is not a very complicated mathematical problem because it's a combination of linear and nonlinear transformation. In principle, it's straightforward, but on the practical point of view, that there are ways that are more efficient than others to compute these gradients. And Filippo will describe approaches based on what people call automatic differentiation. These are, if you want, a way to efficiently compute these gradients automatically, typically using codes, and in a way that will scale with the same complexity of computing the value of the function for a given input. Okay, so essentially there's a prefactor that Filippo will explain to you. But so the complexity of computing these gradients is exactly the same as computing the function f of x for a given x. So I will conclude here. So and already in this afternoon I will tell you more applications of these ideas or some of these ideas to quantum physics. Okay, thank you.
Okay, thank you very much. I think we have time maybe for 1 or 2 questions. If you have questions, comments.
Sorry, I don't understand in this analogy. Who is there? There with the arrow above.
So
the arrow in a P.
Yeah, sorry. As I was mentioning here, yeah. So these are the R's. So I'm saying that in the Langevin equation, you have a stochastic differential equation for the particle positions that here I'm calling R. So I have particles in I don't know, in 3D or whatever dimension you like, and I have n of them, and they evolve with this equation. Okay, so they move according to Newton force plus noise.
Okay. So if there are no other questions, yeah, Dimmy? Yeah. If there are no other questions, maybe we go together. So we thank again Professor Carleo, and
so hello, welcome back for this afternoon section. Just a little announcement for those who have been here last week, or even for those who haven't been here last week but are curious to know what we did last week. So if you go to the web page of the school, you see like in the section in the folder documents, like all the materials, the slides, lecture notes, handwritten notes of the speakers are available. So like as promised, like many of you have asked to make the material available. So if you have been here last week, or if you are curious what happened, so just go to the web page of the school. So finally, I'm super happy, and it's my pleasure to introduce Sinho, who is going to spend a few days with us. So Sinho comes from MIT, and he's going to talk about the log-concave sampling. Sinho, thank you very much.
Thank you. Also, thank you to Augusto and Simone for organizing this, of course. So I'll be talking about the subject of log-concave sampling. It's going to be based on this book that I'm currently writing that you can find available at my website. So like all the contents of the lectures can be found here. We'll cover maybe, I don't know, like 10-15% of this. So if you're interested in this, then afterwards you can read the rest of it, email me corrections, and so on. Yeah, no, of course, like interrupt me at any time if you have any questions. Okay, so let's start by setting up this problem of sampling. Okay, so we're given a density. And in this course, the density is always going to be written pi. And we're going to say that it's proportional to e to the minus v, where v is the potential function. It's a function from Euclidean space to the reals. Okay, so we're going to write it in this way because actually the properties of v are going to be quite important for understanding this sampling problem. And although like this is supposed to be a probability density, I'm also going to abuse notation and think of pi as a probability measure. This is a common abusive notation in optimal transport. Okay, so we want to be able to draw samples from this, but what do we have access to? We can evaluate the potential at a point x and its gradient. Okay, so this is the information that's available to us in order to design our algorithms for sampling. And then we want to be able to sample while making as few of these computations as possible. And then what is the goal? This is the goal of sampling. We want to output a random variable x. This will be our sample. And if the law of this random variable is mu, then we want mu to be very close to the target distribution pi. In some notion of distance, we'll like see what notions of distance make sense as we go. Right. So is the problem clear to everyone? Okay, so this is a basic task, similarly to how optimization is used for a lot of downstream problems. This sampling task is also used everywhere, but let me just list a few applications, and then I'll go over like a Bayesian example in detail. So of course, one of the primary motivations for understanding sampling is to be able to do Bayesian inference. We'll discuss this in a little bit more detail in a couple of minutes, but basically, like, in order to do Bayesian inference, we have this posterior distribution. It's going to be some high dimensional distribution. But because this posterior distribution, like in order to actually do anything with it, for instance, you want to compute integrals of test functions against this posterior, or you want to build confidence regions or so on, all of that requires being able to access the posterior in a useful form. And a useful form for the posterior is being able to draw samples from it. He also mentioned the ideas from sampling have also been used quite a lot recently for the problem of data privacy, but I won't cover that at all. Another place where this kind of shows up is if you want to study statistical physics, then like the equilibrium distribution of your state according to thermodynamics is going to be this like Boltzmann distribution. And then if you can understand how fast it takes for algorithms to converge to this like Boltzmann distribution, that also tells you important information about your system and so on. So like all these ideas are related to that. Okay, so let's begin with the Bayesian logistic regression example. Okay, so through this example, we're going to see like how you set up a problem using like the framework of Bayesian statistics, and then why sampling will enter the picture. So suppose that we've collected some data. Xi, yi. These xi are just going to be, this is like a vector of covariates that tells you like important information about the ith member of this like set. For instance, like this might be a list of features that corresponds to the ith patient in a clinical study. And we're going to think of yi as a binary outcome. It's either 0 or 1. And for this example, we're going to think of these covariates as fixed, known in advance. And the yi are going to be the random quantities that we're interested in. Okay, so, and then we're going to set up this like logistic model. So let's posit that each yi is going to be independent and drawn from a Bernoulli distribution. And this Bernoulli distribution is going to have the following parameter. Oops. Okay, it's a exponential, it's a Bernoulli distribution with some parameter which depends on this theta. So theta is unknown, and this is what we want to infer. So what you should think of is, as if x is really correlated with theta, then this probability is almost 1. And if x is really like anti-correlated with theta, then this probability is almost 0. So what does this look like? Okay, so just as an example, imagine that yi is the effectiveness of a drug. So 0 means that the drug was not effective on that patient, and 1 means that the drug was effective on the patient. Okay, and what I'm drawing here, these are the xi's. So there are some covariates living in some high dimensional space. And for each of these points, let's label it according to whether or not the drug was effective. So maybe I should use a different color for this, or this corresponds to the drug is effective. And down here, like these correspond to patients for which the drug was not effective. So if your data looks like this, then there's a clear separation. So this kind of tells you that based on the vector of covariates for your patient, you can kind of predict in advance whether or not the drug will be effective. We want to be able to like develop this classifier, right? And what is this vector theta? Theta represents like a linear separator. This might be the optimal theta that we want. So then what if you could find this theta, then what it would tell you is you get a new patient, you compute the inner product of that patient's covariate vector with this theta, and then that gives you like a prediction of how likely that drug is to succeed or not. Okay, so this is the kind of problem that we want to solve, but let's try solving this with a Bayesian perspective. So if we want a Bayesian perspective, then we're going to view this parameter theta as random, and then we're going to put a prior on it. And a very simple choice of prior here is just going to be the Gaussian distribution. Centered at 0, and let's say with variance equal to lambda inverse times the identity matrix. Okay, so now let's write down what the posterior distribution looks like. By the way, is everyone familiar with basic statistics, or? Okay, let's write down what the likelihood is. Okay, so what is so given a value for this parameter theta, what would be the probability of seeing the outcome yi? Remember, like I'm only putting y here because I'm treating all the xi's as fixed. Okay, so you can write this probability as follows. Like so, okay, because if I set yi equal to, sorry, give me a moment. Yeah, okay, so if I set yi equal to 0, then this term vanishes and I only get 1 over 1 plus x of theta xi. So that's the probability of this Bernoulli random variable coming up 0. And then if yi equals 1, then I only get this term. And then that's the probability that the Bernoulli random variable is 1. So this is just a concise way of writing down the distribution of that Bernoulli. Let's continue. Okay, so now if I look at the probability of all the outcomes, then because I'm assuming that all these outcomes are independent across patients, it's just going to be the product. And then finally, to do Bayesian statistics, I have to form the posterior distribution. The posterior distribution is going to be the density of the parameter theta given the data that I've seen. Okay, so this is going to be proportional to the following quantity. So first I take the likelihood, and then I'm going to multiply by the prior. So if I take the likelihood and write it in this exponential form, it's going to look like this: log of 1 plus x. Okay, this comes from the denominator in that expression. And then I have yi times theta xi. That's from like the second term up there. And then I have the prior, which is lambda over 2 times the norm of theta squared, because that comes from the Gaussian density. Okay, and this whole expression is what I call x above minus v of theta. Okay, so this is our posterior distribution. So for this Bayesian logistic regression problem, what you can check is that this function v is convex. In fact, like it's strongly convex. Because of the Gaussian prior, it regularizes this. So it's strongly convex, and that means we know a lot of methods to minimize v. For instance, you can use gradient descent. Okay, and what does it mean to minimize this potential? It means you're finding the mode of this distribution. And the mode of the posterior distribution is known as the maximum a posteriori estimate. Okay, so what does this do? This summarizes the entire posterior distribution by a single point, which is its mode. And although it's like easy to compute, it doesn't really capture the full distribution, right? And like the point of doing this Bayesian inference is so that we don't just take a single value of theta star, but we want to start to understand like the amount of uncertainty in this posterior to try to get like some confidence estimates and so on. So what we really want to do is to be able to like sample from this entire distribution. And that's exactly where the sampling problem comes in. So you can see it fits this sampling problem I wrote above. It's some density on RD. We have this potential function V, and this potential is very explicit. Given any value of theta, I could easily evaluate what this potential is. I can also compute its gradients. But just because I can compute the potential and its gradients, it doesn't mean it's necessarily easy to sample from this distribution. So the first thing to notice is that here this symbol is like up to proportionality. So there's like a normalizing constant that divides this whole thing in order to make it integrate to 1. So it's a valid probability density. This normalizing constant is going to be some high dimensional integral because it's the integral of this whole expression over theta. And like computing these high dimensional integrals is challenging algorithmically. Like maybe the most naive thing you would do is try to grid your space, but then the size of this grid is going to scale exponentially in the dimension. So it's not going to be possible to do this in any dimension larger than, I don't know, 7 or something. Yes.
I'm not quite getting what you gain in this case where everything is, where the potential is strongly convex, what you gain in sampling it. I mean, why isn't just the maximum a posteriori sufficient?
It's a good question. So like, why do we actually want to sample from this? Because like just a single point estimate doesn't actually tell us about the spread of the distribution, right? It could be like there's one mode of it, but if the distribution is really spread out, then does the mode really tell you much about it? Yeah. Yeah, and just in general, like we want to be able to we want to be able to do these like uncertainty estimates. Like if you imagine, for instance, like the discovery of the Higgs boson or something, right? In order to actually like make it to the press, they need to be, I don't know, like 5 sigma confident or something like that, like 99.9999% confident that it's true before they can actually report it to the media. So how are they actually like that certain? They need some kind of model that will tell them about what is like the probability that your estimation is actually correct.
It's like not being interested only in the ground state of the system and in the whole behavior of the system, like to understand the second moment and so on and so forth. So this is okay. So
Yep,
if I try, if I can speculate, the problem is calculating the partition function somehow. Am I right? So that's the
kind of, yeah. It's very related to understanding the partition function, and that's also why like the sampling problem is important in statistical physics.
okay.
But actually, like for the sampling itself, even if I did know the partition function here,
Mhm.
it's still not obvious how we would use that to draw a sample from this
Oh yeah,
distribution.
yeah, okay, okay.
So we're
Yeah,
actually
for
like
sure.
the sampling methods we are going to develop are going to bypass the computation of the partition function and just sample it directly. In fact, it goes the other way around, that the currently like the best ways we know of calculating the partition function are to sample and then use these samples.
Okay, okay.
Yeah.
Thanks.
You and Andrea share this one.
Ah, okay.
Are there any other questions? And so we're all good with like what a sampling problem looks like, and okay. So how do we actually do the sampling? We're going to run a Markov chain whose stationary distribution is the posterior that we want. And then we run the Markov chain, but like the point of this course is like we really want to understand quantitatively how long it's going to take for this Markov chain to converge. Not just asymptotic results, like if you run the Markov chain long enough, then it will converge. So that much is obvious. But what we want is to be able to quantify it in the same way that we've been able to quantify all these results for optimization. For an optimization, we know like very precise complexity estimates for how long gradient descent is going to take to converge. I guess like you've seen a course about this last week, some of you. And then we want to do the same for sampling, but sampling is going to require like not just the understanding of optimization, because there's going to be a lot of connections between optimization and sampling, but it's also going to require some new tools such as like probabilistic tools about Markov chains and optimal transport and so on. Okay, so we're going to discuss a lot of parallels between optimization and sampling. So in optimization, we want to minimize V. Just find the ground state of the potential. And then in sampling, we want to sample from this density pi. Okay, so in optimization, the most basic thing you can do to minimize V, let's even starting continuous time, is to follow the gradient flow. And what is the gradient flow? The time derivative of xt is just minus the gradient of the potential. Okay, and then in order to do sampling from this distribution, so this gradient flow is always going to converge, let's say, to like a stationary point of this function b. But in sampling, we don't want our point to just converge to like a single location. We want it to kind of explore a lot of different regions, so we need to add some randomness. And so the analog of this gradient flow is going to be what's called the Langevin diffusion. This was also introduced in the morning lectures. And it's the solution to a stochastic differential equation. Here, this is the Brownian motion increment. Okay, and the reason why this diffusion is natural is because it has stationary distribution pi. But in order to study this, we're going to really need all the intuition from optimization and transfer it here. So to kind of spoil the punchline a little bit, one of the key facts about this diffusion is, well, I guess if you look at it, it looks like a gradient flow just from this term, but we've added some noise because of the Brownian motion. So it looks like a noisy gradient flow. But what we're going to see is that we can actually interpret this diffusion not as a noisy gradient flow, but as an exact gradient flow. And the way that you do that is, instead of looking at the level of the particle is bouncing around everywhere. It has very irregular movement because of the Brownian motion. What we're going to look at is the law of the diffusion at time t. So now when you look at the law, it's an element of the space of probability measures. And the evolution of the probability measure is going to be a lot more regular than the evolution of the individual particle trajectory itself. Yes?
To me. Oh, okay. No. I just to see if I am inside the theme. Are we? I mean, what you are saying that we will use, if it's a spoiler, the Fokker-Planck equation of this Okay. Okay. Perfect.
Yeah.
Thank you. I mean.
Yep. So the Fokker-Planck equation is going to govern the evolution of the distribution of this diffusion. We'll derive it. But also we'll see that this Fokker-Planck equation can be viewed as a gradient flow on the space of probability measures. This is going to use the differential structure of optimal transport. And it's going to follow the gradient flow of the KL divergence, the Kullback-Leibler divergence to the target distribution pi. So now there's going to be this very interesting geometric interpretation of this diffusion. And it's also going to help us design new algorithms for sampling. But before that, I guess I want to talk a little bit more about optimization so we're all on the same page. Yep. Yep. Okay, so let's talk about what conditions that you can place on the function b in order to study the optimization problem. So the most basic property is that of strong convexity. So alpha strong convexity just says that the Hessian of v is lower bounded by alpha times the identity at every point. You can also reformulate this in a way that doesn't require second order differentiability, but this will be good enough for us. And this condition actually implies something which is called the Polyak-Lojashevich inequality, or PL inequality, also called a gradient domination condition. And this says that the norm squared of the gradient at any point should upper bound the objective gap. Okay, so this condition tells you that the gradient flow will never get stuck because the rate of decrease of your objective gap is precisely this minus norm squared of the gradient. And then this is saying you will always make progress. Okay, so these two conditions, so strong convexity implies the PL inequality. Yeah, let's write that here maybe.
Sorry, Sinho, but there is some alpha somewhere in the PL.
Sorry, yes. 2 alpha. Okay, so let's quickly see why. Yeah.
Sorry, I don't understand one thing. Why maximizing V is needed to sampling? Or
Sorry, what was that?
as I have understood, the maximizing V is needed for sampling, but is this true, or I don't have understand?
Is what for sampling?
Maximizing V.
maximizing?
Minimizing V.
Minimizing V.
Yeah.
Why is that related to sampling?
Yeah. Exactly.
So like basically we're going to like how do you study sampling? We're going to take an understanding of optimization and try to draw analogies with it when we study sampling.
Okay. Good.
Because like sampling is going to be optimization just in a more abstract space, the space of probability measures. So like I want to kind of understand the optimization concepts and then like use that for sampling.
Okay. Thank you very much.
Okay, so let's review why strong convexity implies the PL inequality. So a consequence of strong convexity is that if I apply the strong convexity inequality at x and x star, then I have this from strong convexity. And then now if I lower bound this inner product term using Cauchy-Schwarz and Young's inequality, then I can lower bound by one term that looks like 1/2 alpha times the norm of the gradient squared, and another term which is going to be minus alpha/2 times this difference. Okay, and you can see like I chose the coefficients in Young's inequality so that this term will exactly cancel this term. And then when you rearrange this inequality, you get the PL inequality. Okay, so this is a weaker condition than strong convexity. And in continuous time, the PL inequality is going to imply that the gradient flow converges exponentially fast in objective gap. And strong convexity is going to imply that we actually converge to the minimizer. Okay, so this is, I mean, you cannot get convergence to the minimizer under just a PL inequality, because a PL inequality, you might actually have multiple stationary points. For instance, like the constant function 0 is going to satisfy a PL inequality. And if that's your function, you will indeed converge very fast in objective gap, but there is no unique minimizer. So you have these two statements, right? And do we all like recall like why these are true? This is continuous time, so you can just differentiate. If I differentiate, let's say like if I differentiate the distance to the minimizer, I get this term, and then also the gradient flow travels according to the minus gradient at xt, and then you apply strong convexity, and you get this, and then you're done. And similarly for the objective gap under a PL inequality, if I differentiate this objective gap, I will get the inner product of the gradient times the derivative of xt, which is minus the gradient. This is minus norm of the gradient squared. And then you can apply the PL inequality to this, and then you will get exponential decay in the objective gap. Okay, so this is pretty simple. Are there any questions about the continuous time understanding of gradient flows? No? Okay. Okay, so this is all in continuous time, but we also have to consider what happens in discrete time. Okay, so to actually like discretize the process, we need something more than just strong convexity or PL. We also need like smoothness. So this is a new consideration in discrete time. And smoothness is just going to say that the Hessian of the potential is upper bounded by beta. Remember, it's like lower bounded by alpha under strong convexity. I guess to be more general, in the non-convex case, we want to say that the operator norm is at most beta. Okay, and then when we have this assumption, then the scale invariant quantity that governs the rate of convergence is the condition number. It's the ratio of the smoothness to the strong convexity. Okay, so when you have this, then you can look at the gradient descent iterates. With some step size h. And under smoothness, a good choice of step size is actually just 1 over the smoothness. Okay, and then for this, we have, in the strongly convex case, convergence to the minimizer at a rate of, okay, I should probably use less confusing notation. You have a convergence to the minimizer at a rate which depends on the condition number. And then under the PL inequality, you also get convergence with the rate that depends on, okay, where here like kappa is still the ratio of beta over the PL constant. Okay, so what this tells you is that for optimization, we know how to discretize very well. As soon as you have the smoothness condition and you choose a step size accordingly, then you get exactly the same results that we had in continuous time, but for the discrete time algorithm. So I guess you had a course on optimization last week. Do you remember how to get these results? Who needs like a review on how to get these results in discrete time? Okay, let's do it then, because these principles are pretty fundamental. Okay, let's start with the PL case. So first of all, what does smoothness tell us when we apply it to, okay, why is smoothness important here? We need smoothness because like in this algorithm, we're following the gradient at xk, but we want this gradient information to be accurate. If the gradient is changing extremely rapidly, then this gradient information is almost useless to us, right? So we need some like control on how fast the gradient changes so that the algorithm is doing something useful. So this, what we'll do is we'll start by applying the smoothness inequality to derive a descent lemma that will tell us how much we gain in the objective value for each step of gradient descent. So if you apply the smoothness to xk, or sorry, t and xt, you get this inequality. This is the smoothness inequality. And now this guy is just the gradient. That is how the iterate is defined. And this norm squared is 1 over beta squared times the norm squared of the gradient. Okay, so if you see, this is going to be minus 1 over beta times the norm squared of the gradient, and this is plus 1 over 2 beta times the norm squared of the gradient. So this one's middle term is going to win, and then we get this. Okay, and this is called the descent lemma. Okay, so what does this tell you? It tells you that your objective value at the next iterate is at most the objective value of your previous iterate minus something that was like the size of the gradient at your previous iterate. Okay, so you descend on the objective value. Okay, so from here, actually the proof of the PL result is pretty easy. So I just look at what is the objective gap at time t plus 1. And then I write this in terms of the objective gap at time t, and then the difference. Now this is how much progress we've made in the objective at the iteration in time t, and that's what the descent lemma tells us. So this is at most norm of the gradient. Okay, but now we can actually just apply the PL inequality directly to this. So the PL inequality lower bounds the size of the gradient. By the objective gap. So you put this together. I have here like the objective gap minus alpha over beta times the objective gap. So this whole thing is at most 1 minus 1 over kappa times the objective gap at time t. Okay, so, and I can also just bound this by an exponential. Is that right? Yeah, it should be right. Okay, so this tells me that from iteration t to t plus 1, my objective gap shrinks by a factor of e to the 1 over kappa, and then I can iterate, and then I get the PL inequality proof. Okay, and then let's do the strong convexity proof. Strong convexity proof, we need to prove convergence to the minimizer this time. So what do? We take the distance to the minimizer, and then we just have to expand the square, because that's the only trick you can do. So you have this term plus the inner product term. And then the third term. Okay, and then let's just rewrite everything in terms of the gradient. This will be minus 2 xt minus x star times the gradient at xt. Step size, there's the step size factor. And then beta squared times, 1 over beta squared times the gradient. Okay, so this is what happens when we take the distance to the minimizer squared and then we expand the square. Okay, now there's like several different ways to conclude the proof at this point, but every single one of the proofs, you want to take this third term and you want to use the smoothness to say that it will kind of get absorbed by the second term. That is the role of smoothness, is that you can like neglect the second order term in your Taylor expansion. And there's like many ways to argue about this. So I had a friend once tell me about like the three cultures of optimization: the American way, the French way, the Russian way. So the Russian way, so the American way is going to be to use the descent lemma, which we'll do in a moment. The French way is to use like a coercivity inequality for the gradient to absorb this into that. And then the Russian way is to like go from here to Bregman divergences. There's like a lot of different ways to do the proof here, but we'll just use the American way, because I'm from America, and also like we already proved the descent lemma. Okay, so what does the descent lemma say? Okay, so the descent lemma is for this third term. The descent lemma says that the gradient is upper bounded by 2 beta times v of xt minus v of xt plus 1. Okay, so this is what the descent lemma says, but in particular, this gap is at most what I had for the objective gap if I put the optimal v star here. Okay, so when you apply this, this is going to be at most 2 over beta times the objective gap. Okay, now what about this middle term? If I apply the strong convexity inequality, so this is convexity. That's good because I have the same term here that's showing up here. But strong convexity also lets me win an extra term. Okay, so if I rearrange this, sorry, this should be x star minus xt. This is equivalent to saying this inner product term here, which is the thing that I want to upper bound. This is upper bounded by minus the objective gap, and then also minus this quadratic term. Okay, now you see the magic that happened is when I multiply this term by 2 over beta, then the upper bound I get 2 over beta times the objective gap, and that will exactly cancel with my upper bound on the third term. And I still win because I have the strong convexity term left over. Okay, so to conclude, the distance to the optimizer at time t plus 1, I have 1 copy of it here, and then I subtract 2 over beta times alpha over 2, which will give me, again, like a 1 over 1 minus kappa factor. And then we're done. Any questions? Yes?
Can you repeat how you use the... So for the smoothness, you have the upper bound in the Hessian, right?
Yes.
This is equivalent to Lipschitz continuity on the gradient?
Sorry, where did I use Lipschitz continuity?
No, I'm asking, is this equivalent to Lipschitz continuity over the gradient?
Yes, yes, that is correct.
And then, okay, yeah.
So let me just write it here that if this thing is bounded by beta, this is equivalent to, let's say like grad V is beta Lipschitz.
Yeah, exactly. And then how do you use this smoothness? That I could not see in the board when you wrote the step that uses the smoothness.
So I really only used a consequence of smoothness, which is this descent lemma.
Ah, okay, but you
And
just
this
included
descent
there.
lemma was derived using smoothness.
Okay, I see. I see. I mean, it's very nice because you get the exponential convergence for the explicit Euler, that is the descent that you, so the discretization that you put there. But for example, if you use the implicit one, you can relax the condition of the smoothness, right?
Correct. If you use implicit discretizations, you don't need smoothness at all.
You know, then you get exponential convergence. Okay,
Yeah.
thank you.
Any other questions?
So just to wrap up, so we've showed that we have shown that smoothness implies the PL inequality.
Sorry, strong convexity implies the PL inequality.
Oh, okay. So the strong convexity. Oh, okay, makes sense now. Okay, and then there the descent lemma is just a consequence of the smoothness. Am I right?
Yes.
Okay, so descent lemma. So and then the last proof is the one which showed that the strong convexity is something that you can derive from from using the descent lemma. Am I getting it right? I'm a little bit lost in the flow of.
Right. Okay. Let's summarize. So, strong convexity implies the PL, and we said like in continuous time, PL implies objective gap convergence, and strong convexity implies convergence to a minimizer.
Okay.
If you want to then translate these continuous time results to a result about the algorithm, we need to add smoothness.
Okay, because here we work in discrete time, and okay.
Then we added smoothness, and then we showed that like if you add smoothness, then under strong convexity and PL, you get the same kinds of results that you got in continuous time, but now for the discrete time algorithm.
So if I had a smoothness under strong convexity and PL, I get exactly the same rates as in the continuous time.
Sorry, you get these rates. These rates over here.
Oh, okay.
And these rates are like slightly different from the continuous time because they involve this condition number kappa rather than just the strong convexity parameter.
Okay.
But like in discrete time, you should expect all your results to depend on the scale invariant parameter kappa.
Okay, perfect. Thank you very much.
Yes.
It's possible to relax the strong convexity condition for example, coercivity and Lipschitz continuity?
To coercivity.
To relax the lambda convexity condition?
Yeah, I guess there's all sorts of relaxations that you can do from this point. But yeah, I guess I'll probably just stick to this as like the most basic template of how you do an optimization proof.
Yeah, okay.
The PL condition is already like relaxing from strong convexity. So the PL condition, I haven't shown to you that this is the case, but it includes functions that look sort of like this. It doesn't have to be strongly convex, as long as this is not exactly flat, but like, yeah.
A related question. So if I got correctly, with the decreasing lemma, you have also you have always the power 2. What happens if in the Polyaklos in the PL inequality you have an exponent which is not to all the magic disappears?
Right. So if you don't have an exponent 2 on the gradient, then this is the more general family of inequalities, I guess also maybe called like KL inequalities or something. But in those will like give you different rates of convergence than exponential. Like you might get polynomial decay with the time horizon. So the way to understand that is like if you just look at the continuous time and then you plug in like those other assumptions, and you get other kinds of differential inequalities, and you solve them to see like what the rate should be. Yeah, but yeah, the PL inequality works very nicely, as you can see, if you want exponential convergence. Okay. Okay, so let's return to this picture of optimization and sampling. So for optimization, for the gradient flow, what we did was we looked at these two conditions, strong convexity and PL. And then we showed that, well, they lead to convergence in the gap and convergence to the minimizer. Okay, so that was the continuous time theory. What we want to do is follow this exact same path, but for sampling. So like what is like strong convexity here, and what is like a Poljak-Loješević inequality for sampling? But so far we haven't really been able to state what these conditions are for sampling. So the plan, I guess, in like the rest of this lecture and the next lecture, we're first going to study the continuous time theory of this diffusion. And when we study the continuous time theory, we're going to see what should be the analogs of these conditions. And then just as we went from the continuous time to the discrete time, we need to understand the discretization of this process. But one thing to foreshadow now is that there's actually something really interesting that happened with these optimization proofs. It's that like the discrete time really reflects the continuous time, just with like the rates change appropriately. In particular, these optimization algorithms are what we would call unbiased. Like they converge to the true minimizer even in discrete time. There's no like error that you make here. But that's not going to be the case in sampling. When you discretize this stochastic process, actually the stationary distribution is going to change because of the discretization. And when the stationary distribution changes, now the algorithm is biased. And then so we're going to get like slower convergence rates for sampling. Another thing to mention is that these rates for optimization are all dimension independent, in that like the problem dimension didn't appear anywhere. In fact, all of these proofs work in a Hilbert space. But for sampling, when we discretize this Brownian motion, now we're going to get terms that depend on the problem dimension. So sampling is going to be much more expensive due to this dimension dependence. Right. Okay, so let's derive the evolution of the distribution of the Langevin diffusion. This is the Fokker-Planck equation. Okay, so right now we're going to derive a PDE for the law of the Langevin diffusion. That's the Fokker-Planck equation. But we'll probably have to wait until tomorrow to actually interpret this as a gradient flow in the space of measures. So I guess the next lecture will be devoted to trying to set up all this Wasserstein calculus. For now, like this PDE, if you've never seen it before, may not mean much, but it'll gain an interpretation soon. Okay, so pi t is going to be the law of the Langevin diffusion at time t. Okay, and then we want to understand how does this law evolve? Yes. So zt is a random variable because it's driven by Brownian motion. It's a random quantity, and this is it's like probability law. It's distribution. Okay, so how do we derive this PD? We're only going to derive it formally, so I'm not going to do all the technical details, but what you can do is like ask how does a test function evolve along this diffusion? And then if you can understand how test functions evolve, then by duality, you can understand how the law evolves. So let's say this is going to, phi is going to be some smooth test function. And then let's just try to understand, well, what we really want is the time derivative of this test function along the Langevin diffusion. If we can understand this for every test function, then somehow we've understood the Langevin diffusion. But let's kind of work heuristically and let's say, so for t very small, let's just formally expand out this quantity, an expansion with respect to the time variable t, and see what happens. So the Langevin algorithm, it looks like I take a gradient step, and then I have this Brownian motion. So the increment of the Brownian motion can be written as square root 2 times xi, where xi is going to be a standard Gaussian. Okay, so this is kind of imprecise, but as t goes to 0, then this is like the correct intuition for what the Langevin diffusion is. So we'll just plug this into here and then expand everything in terms of t. And we'll think of z0 as fixed. Okay, so if you expand this out, first you have the first order term, and then you have the 0th order term, and then the first order term. And then the second order term. Okay, so by the way, like if you've never seen stochastic calculus before, then this computation gives you like the intuition for like why stochastic calculus is founded essentially. If you have seen stochastic calculus before, then you're just going to be crying because all these calculations are extremely non-rigorous. Okay, so the first thing is like, as t goes to 0, why isn't this second term blowing up? It's scaling as square root t, which is much bigger than t. So why is it not blowing up? The reason why is if you look at this expectation, then this term cancels out because the Gaussian is mean 0 and independent of z0. So it doesn't actually appear. That's why like it's okay to have the square root t there. That's also why we need to go to the second order expansion, because the square root t, it's going to be like the second order expansion. If you look at the square root t Gaussian, square root t Gaussian, now you have an order t term, so it's no longer like negligible. If we were just doing regular calculus, we would be fine just expanding to first order to find this time derivative, but now we have to go to second order. So that is like the idea behind Ito's formula. Okay, so we're only going to collect terms that are like order t. So here we have one order t term here. That's like minus t times times this term. Now, if you expand out this square, then the only term that's order t is coming from the two Gaussians. So we get a plus t times the expectation of, oops, sorry, this should be a Hessian. Okay, then we get the quadratic form of the Hessian at z0 with the two Gaussians. Now this term is the same thing as the inner product between this Hessian and this outer product of Gaussians. And this outer product of Gaussians, when you take the expectation, is just going to be the identity matrix. So when you take the inner product with the identity matrix, you get the trace. And the trace of the Hessian is also called the Laplacian. So you get the Laplacian. Okay, so what does this show? It shows that the expectation of phi of zt is equal to phi of z0 plus t times two terms, the Laplacian of phi at z0 minus the inner product of phi and the gradient of v plus little of t. Okay, so now this quantity in braces is really important. It's called the generator. So the generator is an operator, a linear operator that maps functions to functions. And we just computed the generator of the Langevin diffusion. It's this second order differential operator. Okay, and what we also saw is that the time derivative of the expectation of any test function along the Langevin diffusion is given by the expectation of the generator of this function. And this is one of Kolmogorov's equations. Okay, so this is like maybe the starting point for a subject called Markov semigroup theory. So you can encode the dynamics of Markov processes into like these linear operators, like a semigroup. I don't think I'll really talk much about Markov semigroup theory because maybe it will take us too far afield, but this is like a pretty important topic. Okay, instead let's just use this to derive a few consequences. Okay, so suppose that, okay, stationarity. Suppose that we initialize the Langevin diffusion at its stationary distribution. Yes.
Sorry, how did you get the Kolmogorov equation? Sorry, in this context, I haven't quite get it. Like you derive with respect to time, this one. Oh, okay, I see.
Right, so if I take this, I subtract phi of d0 from this side, divide by t, let t go to 0, I will just get this part.
Okay, but I'm not seeing the expectation value over the L? Because like if you did just with the derivative with respect to t, right? Why have you insert another time in the expectation value?
Right. So here I did this computation assuming that z0 is fixed. But then like in general, like when you have like a random initial condition, then you need to take the expectation with respect to that.
I see.
Yeah.
Okay. Thank you.
No. So the two expectations are different, right? So the first one is with respect to the law of ZT, but the second one is with respect to the initial distribution. Right?
Yeah, but it's still the law of ZT. Yeah, so it's actually the expectation with respect to the same law. In order to compute the time derivative of this expectation, you have to look forward into the future. So then you get expectations with respect to the Brownian motion increment. But as the time on which you do this computation tends to 0, then it's like the expectation value at the same point.
If I may add, so I guess the computation you did is like conditionally with respect to ZT equals something, and so it's just, as you said, the expectation with respect to the noise. But then in order to calculate the derivative of the expectation of phi ZT, then you have to you have to do the expectation with respect to ZT. And so the two expectations are the same, but inside there is in order to do computation, there is the conditionality and there is just the noise.
Yep. Yeah. Sorry for not explaining it clearly. Okay, so the first thing I want to note is from this is like, let's suppose I start this diffusion at the stationary distribution. So the stationary distribution of the Langevin diffusion is this distribution pi e to the minus v that we want, but I haven't shown you why this is the case yet. So before we know that it's true, let's say that the stationary distribution is some pi tilde. Then if you start at stationarity, what this means is that at every time you have the same distribution. That's what it means for the process to be stationary. So in that case, these expectations should not be changing with respect to time. Right. So then if you apply that to Kolmorov's equation, then what that tells you is that for the stationary distribution pi tilde, you have expectation under pi tilde of the generator of phi is equal to 0 for all functions phi. Okay, and this is a characterization of the stationary distribution. Okay, but we can do more than that because like since we have the evolution in time of the expectation of every test function, we can now write down what is the evolution of the density itself. Okay, so let's write this in integral form. This is the time derivative of the integral of phi with respect to the law of ZT, which remember I'm calling it pi t. And yeah, so like let's pretend all the densities are smooth and everything, which you can get by like elliptic regularity. So this is really just a density, and this is a Lebesgue integral. Phi is not changing with time, so we can kind of bring this time derivative inside the integral. And then we get the time derivative of the density. Okay, and this is what we want to find, the time derivative of the density. But on the other hand, if you look at the right-hand side of Kolmogov's equation, then we we have another expression for what this time derivative is. It's the integral of the generator applied to this test function phi integrated with respect to pi t. Okay, so we want to match this expression with the one up above. So what we need to do is we need to bring this generator off of phi and onto pi t. So in other words, we need to look at the adjoint of this. Okay, but remember we have an expression for what the generator is. It's the Laplacian minus the inner product of the gradient with phi. Okay, integrated with respect to pi t. And now to compute the adjoint, we're going to integrate by parts in order to bring all the derivatives off of phi and onto pi t. So when you do this, you're going to get Laplacian pi t plus, wait, no. Yeah, it's plus, right? Plus the divergence of grad v times pi t. Okay, so this is by integration by parts. Okay, so now if you have this equality for every test function phi, then you can also equate directly what these two are. So then we have the Fokker-Planck equation. The time derivative of the density is given by the Laplacian plus the divergence of grad v times pi t. Yes.
So with the first, okay, so you are with the Laplacian, you are integrating by parts twice. Am I getting it right? Okay. And then with the other part, okay, I understand the step for the, why are you not doing, I mean, the gradient of V, why does it remain the same? I would have also,
well,
I'm not seeing this very, at the moment, maybe I have just to think about it a little more.
So you should think of this as like the product of grad phi and then pi t times grad v.
Yeah.
So then I move the derivative off of the phi, and then I put the derivative on the everything that remains, which is grad v times pi t. And in this case, like because it's a vector calculus, the integration by parts gives me a divergence.
Okay. Okay.
I guess you could also write it as grad times grad. Okay, so let's also rewrite this. Yeah, let's rewrite this in another form, which may be like better for interpretation. So the Laplacian of any function can also be written as the divergence of the gradient. So when we apply this, then this Laplacian of pi t, we can write both terms as a divergence. Oops. Then this is divergence of the gradient of pi t plus grad v times pi t. And then we'll do one more step, which is the gradient of log of phi is just the gradient of phi over phi. So I can rewrite the gradient of pi t as pi t times the gradient of log pi t. And the reason why I want to do this is so I could factor out this pi t in front. And then I get grad log pi t plus grad v. okay, so what does this tell me? If I set this whole equation to 0, that will tell me the stationarity, right? The density is no longer evolving in time. So how do I set this whole thing equal to 0? Well, I can just set this part equal to 0. Okay, and if I set this part to equal to 0, this is telling me that grad log pi t should be like minus grad v. Let me see if I could use this space. Okay, so for stationarity, we want grad log pi t to equal minus grad v. So a natural choice would just be, can we make log of pi t equal to v plus a constant? Or sorry, minus v plus a constant. And then you exponentiate both sides. And then this tells you that for stationarity, we want the density to be proportional to e to the minus v. So this tells you like why the density e to the minus v is actually stationary for the Fokker plane.
Sorry, I'm sorry. A little bit. I still struggle a little bit with the. So the Fokker Planck, okay, it's fine for me. But then you are rewriting the Laplacian in terms of the divergence of the gradient, and this makes. I haven't. I mean, I'm lost there. Precisely. Yeah. Exactly.
Okay.
Yeah.
So
what are we trying to do?
Oh, sorry, asking like why I'm using this?
Exactly.
So I just want to rewrite the right-hand side of the Fokker Planck as a single divergence, because this like helps the interpretation.
Okay. So phi is pi. Okay. This is true for every phi, and then okay.
So these are just equal because of some like calculus manipulations. But then when I have it in this form, I can see like if I want to find the stationarity condition, like for the right hand side to be 0, I could just set the sum of these terms equal to 0. And when I set the sum of these two terms equal to 0, I see that the stationary distribution is the density proportional to e to the minus v.
Okay. Thank you.
So in this last step, you're using that you're equating the thing inside the divergence to 0. But something can be not 0 and have divergence 0, right?
Yes, correct. Yeah. Yes, I haven't really justified to you like why there's like a unique stationary distribution.
Okay.
For instance, but actually like what we're going to do next is we're going to like find, because like in order to study sampling, we need to find criteria for fast convergence to the minimizer.
Okay.
So if you converge quickly to the minimizer, in particular, there has to be only one minimizer. So
okay.
But I guess like we'll only show this for the strongly log-concave. Okay, but I'm not going to justify in full detail why the stationary distribution is like unique, but there's like a lot of theory for that.
Okay, thank you.
The special seminar is like the continuation of Giuseppe Carleo lecture this morning, that now we are going to do quantum neural networks. So I welcome you to ask as many questions as you want and enjoy Giuseppe's presence, because he's leaving tomorrow and the course will be continued by Filippo. So Giuseppe, can you?
Thank you very much. I feel now that I am unbounded. Okay, great. So welcome back. So first of all, I wanted to do a little survey of how many of you know some quantum mechanics, or at least the main concepts. So essentially almost everybody, okay? Good, great. Quantum mechanics. No, something like, okay, Schrödinger cat. I don't doubt that, but I mean, I just wanted to be sure. Okay, so let's do a first trip into this into the problem. So what is the main problem that we would like to solve, and then we see how we can use machine learning, right? So first we have to understand the problem. So this will take maybe 5 minutes, but it's okay. So the simplest quantum mechanical object that we can think of is a spin 1/2. Okay, so spin 1/2, or a qubit if you know quantum computing, is something that that is, for example, attached to an electron. So an electron can be either up or down, right? So you've seen this kind of things. So let's say if I have a single spin, all the properties of this quantum particle, if you want, are described by a vector. So I hope that you are familiar with Dirac's Bra-and-Katz notation. Guys, it's a disaster. Okay, so this is equivalent to sorry, hold on. So this is equivalent to this. Okay, so it's essentially a column vector. Okay, and then I will use this. So this object is called a cat. Okay, this object is called a bra. Unfortunate as it is. Okay, so and this is the transpose essentially of right of the vector psi. Okay. And why they are called Bra-and-Katz? Because when you take the inner products, you have a bracket. Okay, so this is psi, and this is indeed just the inner product between psi, the vector. So this is the norm, if you want, of psi, right? And this is yeah, that's why they're called brackets. Okay, so we use a lot this notation in quantum physics to indicate vectors or in general functions.
Square.
Yeah. Well, I didn't say it's okay. It's I didn't say what the norm means. I mean, it might have been whatever you like. Okay? Anyways, great. So this is the crash course in Dirac's notation, and then you can write also operators. But okay, operators are just written as operators. I mean, the only thing is how we write vectors essentially. Okay, so why am I telling you about this? Because if I have now a single spin, so the physical state of this single spin is described by a vector. Okay, so so a vector which has now which has two, if you want, components. Okay, so this vector lives now in a two-dimensional space. And these coefficients, so C up and C down, in general, are complex numbers. Okay, so I have a vector in a two-dimensional complex space. And these are just the basis states. So essentially two orthogonal states that I can pick as basis states. So for example, I don't know, 1, 0, and 0, 1, right? So your unit vectors. Okay, now, so all the properties are contained in these two coefficients, C up and C down. For example, the square of these coefficients will tell you what is the probability of observing the spin in the up position. So the square of C up will be the probability of measuring. So the probability of measuring the spin up is given by the square modulus of this coefficient. And the probability of down, the square modulus of C down. Okay? So you see that there is a constraint because now the sum of these two must add up to 1, which means that essentially I'm working with normalized vectors in L2 norm. Okay, great. One spin. Now, what is the problem? The problem is that if we want to describe the properties of, so let me put a subscript here, psi1, to indicate that this is one spin only. If now I have n spins, the structure of the theory is much more complicated. I mean, the structure is similar, but I mean, not conceptually is not complicated, but practically it's complicated because now, if I want to describe all the properties of this system, I need to specify, if you want, all the components in a basis that is now much larger, actually, because I have to consider all the possible combinations, essentially, of whether I observe the first spin to be up, the second spin to be up or down, and all the others. So I have 2 to the n possible combinations. So for example, I might have, I don't know, C up, down, and then this is my other unit vector that corresponds to this situation. Plus, so you see I have 2 to the power n terms, and I mean, in some ordering, and now I have the last one, which is just where all the spins are down. Okay. So I can also write this more compactly as the sum over k, for k that goes from 1 to 2 to the power of n, of some ck, and then some basis state that I'm calling k just in this compact notation. Okay. So I'm just using, if you want, yeah, I mean, yeah, you can think that k is also a binary number. I mean, I'm just, you can think of this as zeros and ones, and k is just a binary number between 1 and 2 to the power of n. Okay. So you see, the problem is that now, if I want to describe the properties of n electrons, let's say if I consider only the spins, I need to know what are all these coefficients, because yeah, this will contain essentially all the physics of the problem for reasons that now I don't want to enter into, but I mean, they contain all the properties that you want. So great. So this is so these are what we call wave functions. So essentially, these vectors are called quantum state vectors or just wave functions. So these are the main ingredient that contains the physics of the system. And now the second ingredient that we need, so this is again your crash course in quantum mechanics, is how do we find these vectors? Because I only told you that there exist these vectors that describe physical systems. Well, the main equation that we want to solve to find these vectors is Schrödinger's equation, which is nothing but an eigenvalue problem. I mean, at least in the time-independent version. So I want to find, if you want, all the eigenvalues of some operator that I will tell you about in a second, with some eigenvalue ek. Okay, so now H is some operator, linear operator, a matrix that lives in this exponentially large space to the power of n. Okay, and these are the eigenvalues, vectors, and these are the eigenvalues of this linear operator, of this matrix. Now, what are the properties of this operator that, again, is called the Hamiltonian? So the Hamiltonian is, in this formulation for spins at least, an exponentially, so it's a 2 to the n times 2 to the n Hermitian matrix, which implies, of course, that also all its eigenvalues are real. So which means that the EKs, so the eigenvalues are real. And indeed, we interpret these eigenvalues as the possible values that an energy measurement can have. Okay, this is, again, I'm not telling you more than that. But so essentially, if you want, our problem is finding eigenvalues of this operator. And the main issue is that these vectors live in an exponentially large space. That's quantum physics, the problem that we have. Okay, now, to be more specific, since you know, finding exponentially many energies, as we call them, I mean, these eigenvalues is not very physical either. So I will focus on the problem of finding the lowest possible eigenvalue. Okay, so an extreme eigenvalue. So for example, I will classify these eigenvalues in a way that E0 is the lowest energy or the lowest eigenvalue. Okay, so E0 is the lowest possible eigenvalue, and then all the others are sorted in this way. So why this problem is complicated? I mean, you already understood now, because if I try to solve this problem on a computer, unless again the matrix H has some special structure that you know, we can exploit, but in general we don't have this luxury. And if I now try, so if I if you want, write or slash store all the matrix elements of this matrix H, right? In some fixed basis. So, for example, in this basis of unit vectors that I chose at the beginning. Okay. So again, for those of you who are not familiar with Dirac's notation, these are the matrix elements of my operator in the chosen basis that I picked. I don't know if this is clear because I'm just taking the it's okay. Yeah. So these are just the matrix elements of my matrix in the chosen basis. So you see that if I try that, if I just store this object, so I have now 2 to the power of n complex numbers, 2 to the power of n times 2 to the power of n, so squared if you want, complex numbers. So if n is larger than 30 or even actually no, much around 15 already, you will not be able to store this matrix on even a relatively large computer, because essentially you run out of memory and you have too many numbers. Okay, so let alone, I mean, and then even then it's clear that you can't even diagonalize this matrix because you can't even store it. So it's problematic. So we have an issue there that we have to somehow try to bypass, right? So we have to avoid, for example, storing this matrix, and we have to find ways of working with this problem, with this eigenvalue problem, if you want, without storing this matrix, but trying to do something a bit more intelligent, if you want, slightly more clever. And there is an important property of this Hamiltonian matrix that I didn't discuss yet, but that I think that it's extremely important. And it's the fact that we are interested in physics in what we call k-local or local Hamiltonians. So the condition of being a k-local or local in this context means that if now I take this matrix element, k and k prime, and I try to understand which values of which matrix elements are non-zero, when I fix this index k, okay, so essentially this corresponds to fixing the row index of this matrix and asking what are the columns k prime for which these matrix elements are non-zero. Okay, so if you do that, then you can show that for physically relevant Hamiltonians, so for physically relevant problems, the number of non-zeros, okay, so if you want the number of k primes such that this is non-zero are polynomial. So there are polynomially many in n, where n is the number of spins. Okay, so notice that this is a strong reduction over the general structure of an arbitrary 2 to the n times 2 to the n matrix, for which instead you would expect that these non-zeros are 2 to the power of n. Instead, they are only n squared and cube, I mean, like a small polynomial typically of n.
Sorry, because you used the word locality and
yeah, this is locality in the context of quantum information, but it has nothing to do with spatial locality, if you want. Yeah,
it's sparsity.
It's if you want, it's a synonym of sparsity. So so another way of visualizing this maybe is just to look at the matrix. So again, let's say that now I consider again the matrix elements of this operator, of this, yeah, I mean in this basis. Sorry. So as I was saying, now if I fix k, which means that I look at this row, for example, and I just look at the non-zero matrix elements, right? So essentially, most of them will be zero. There will be only a few, like So an exponentially small subset of all the matrix elements that are non-zero. All the rest is zero. Okay. So this is this notion of sparseness. This is, this is what you can alternatively call column sparse matrix. So this means that the total number of non-zero entries is equal to 2 to the power of n times a polynomial of n. Right? Because you still have 2 to the power of n possible rows, but for each row you only have polynomially many non-zeros. Okay. And in turn, this means that this is not a standard sparse matrix because the non-zeros are still exponentially many, but you have still this special property. Okay, so I'm not going to give you examples of Hamiltonians that satisfy this property because, yeah, indeed you are not maybe. Do you want an example or not? One example. Ah, okay, good. No, I thought you didn't like physics. But so a simple example. So a simple example is the okay, maybe this is useful because you will see it also in the tutorials. So a simple example is what we call the transverse field Ising model. Transverse field Ising model. So do you know the Ising, the classical Ising model? I mean, pin glasses. No, that's no. Okay, so it's not a karaoke. I mean, okay, so transverse field Ising model. So we write this Hamiltonian in these ways, but then I will need to clarify all the notation in a second. But let me just write it down. So sum over I smaller than j, and I and j run to n, of some interaction matrix that I will call Jij. So this is a spin glass, if you okay, sigma I z, sigma j z. So I will need to clarify what these are because otherwise you are lost. And then you have gamma sum over a to n again is number of spins, and then I have sigma ix. Okay, so this is the transverse field Ising model, and these Gijs are real valued and also gamma are real valued constants that are given by the problem. For example, you can think that Gij is an interaction graph so this is the classical Ising model, and Gij are just interaction constants. For those of you who know the classical Ising model, and this is called the transverse field because it's a fluctuations transverse to this z direction. Again, this is for physicists. Now, what are sigma z and what are these sigma jz, etc.? So these are just operators that are defined in this space of this Hamiltonian, where the Hamiltonian lives. So this 2 to the n, if you want exponentially large space. So, and this is just a shorthand for something very precise. So, for example, sigma ez is the tensor product of the two-dimensional identity, okay? Or Kronecker product. I mean, these are just matrices with essentially identity until you reach this the I. So here you will have I minus 1 identities, tensor products. Okay, then you have these other two-dimensional matrix, which is the polymatrix sigma z. Do you know polymatrices? I mean, polymatrix is the basis of all two-dimensional. Good, and then you have other identities. Okay, so you will have now n minus I minus 1 identities. Okay, so you see that in total, I have a product of n 2x2 matrices, so that the resulting matrix is 2 to the power of n large. Okay. And sigma z is just a diagonal matrix with +1 and -1. Instead, sigma x is the NOT gate essentially. So it's 0, 1. Okay, maybe I can write. So sigma z is just this 2x2 matrix, which is 1 -1, and sigma x is 0, 1, 1, 0, the NOT gate. Okay. What? No, I chose the basis that I picked at the beginning, right? So this one. Right? So if you want the basis vectors that are the, so okay. So for example, these are all the basis states will be eigenvalues of this sigma iz, for example. Okay. Whereas they will not be eigenvalues of sigma ix. That's why we have to. It's non-trivial to find a basis in which the Hamiltonian is diagonal. So if you do your things carefully, you can prove that this Hamiltonian indeed has this property of being sparse, because as I was mentioning, so maybe, okay, so that's when maybe I wanted to tell you about the properties of this basis. Because essentially so the first term, so this sigma z term, is diagonal in this basis. Okay. So this will give you a delta k prime, and then whatever okay, and then this will give you so let me write like this: sigma I z. So now this is just the eigenvalue times sigma j z. So what does it mean? So what does it mean? So it means that, for example, if k now is so I can also write these basis states like this. So sigma 1z up to sigma nz, where each of these can be either plus or minus 1, right? So you see that essentially now this operator finds, so k is an eigenket of this, an eigenvector of this, with eigenvalues given by the value of the specific spin. So for example, if spin I is up and spin j is down, this would be -1. More or less following? Okay. So you see that this term just gives you the diagonal of the matrix. Whereas the other term, which is this sigma x term, you can show, I'm not doing it in detail, in full detail, but the other term, sigma ix, for example. So this is different from 0. Again, I'm not proving it, but you can do it by yourself, only if k prime maybe it's easier to, okay. So only if k prime is 1 bit flip away from k. Okay, so which means that so for example, if it's okay, so let's assume that k is this one. So it means that I have to take the I spin and negate it. So if it's up, I make it down. If it's down, I make it up. So I put a minus. Okay, I'm not proving it, but this comes essentially from the fact that this is a NOT operation. So if you apply this onto a 1, 0, you get 0, 1, or if you apply it on 0, 1, you get 1, 0. So it flips this bit. Okay. But so because of this, so you see that now, since for each k, I only have one k prime such that this matrix element is non-zero, and I have n of these terms. So I have sigma 1x, sigma 2n, etc. It means that for this specific model, the number of non-zero matrix element is actually exactly equal to n of diagonal plus 1, which is the diagonal. So I have n plus 1 per row. So the polynomial in that case, it's linear in n. Just to give you an example, but if you don't want to go too much to these details, okay. Okay, great. Now, what are we going to do about this? Well, we can use variational methods to solve this problem.
Sorry, just a question. So
yes,
in particular, so the Ising model or the orthogonal Ising model. So in
transfer field, yeah.
Not the transfer field. So the Ising model. So without the transfer,
one, yeah.
So you don't need to go there because it's scalar. It's since it's diagonal, you just care about the coefficient. And so
in the case of the classical Ising model, you would have a completely diagonal matrix. But in that case, the ground state would just be the lowest, the state with lowest energy, and it's only one state if you want, right?
Yeah.
So it would be the lowest number on the diagonal. That would be just the ground state.
Okay. And there you usually use maybe someone, or at least what I saw, you do statistics on that, but
yeah, you can
it's completely orthogonal to this. So this is more in the spirit. Okay, when I have something where the eigenvectors is really a vector, it's not
yes, exactly
as easy as
okay. So classical mechanics is the limit in which instead of having a linear superposition combination of these basis eigenvectors, you only have one state. Quantum mechanics is a superposition, as we call it, so a linear combination of many states. Schrödinger's cat is a bit alive and a bit dead. Instead, a classical cat is either alive or dead, can be both.
So in some sense, this is the simplest example where...
This is the simplest example, if you want, of a quantum many-body system, if you want, many spin systems, yeah. So variational methods. So what does it mean? Well, it means that... So what does it mean in this context? Because I know you are familiar with variational methods. So it means that we want to, right. So we want to write now a vector, psi, that will depend in general on some parameters. Let me call these parameters theta, possibly a large set of parameters. And I want to parameterize, if you want, my coefficients. Again, this goes to 2 to the power of n, but I will parameterize now these coefficients ck with these parameters theta. Okay, so now I'm saying I'm not going to store even all these possible 2 to the power of n ck coefficients, which are the components of my vector in the given basis, but I will parameterize them. Okay? So that's why this is a variational method, because I'm introducing, if you want, a variational form, a parametric form for these coefficients. Then, I mean, how can I restate, if you want, how can I reformulate Schrödinger's equation in a variational form, or if you want, as an optimization problem? Well, you can, if you want, form an object that I will call E of theta, which is the Rayleigh quotient associated to this Hamiltonian operator, to this operator. So let me write it down in, if you want, in brackets notation. But if you are confused, I will rewrite it as in the standard way. So I will. So maybe instead of writing like this, I think it's easier if I put the theta here, so that I don't. I simplify a bit the notation. Okay, so this is the Rayleigh quotient. Okay, so Rayleigh quotient means that I take the product of my matrix with my trial vector, if you want, with my parameterized vector, and I take the inner product with itself, and I divide by the norm of the vector. And you know, by the variational principle, I will show it in a second, that this is larger or equal than the exact eigenvalue, the lowest eigenvalue. This is the variational principle in quantum mechanics. So how do we prove that? It's fairly easy. So what we can do is that we can write E of theta. I can insert two completenesses here. So some nice property of the Dirac-Ket notation that I'm not proving, but I leave it as an exercise, is that the identity operator can be written as the sum over k, so where k goes from 1 to the power of n in this space of this object, which is a projector, if you want, sum of projectors. Is it okay? Okay, so now since this is the identity, I can put it everywhere I like. For example, I can put it here and here. So I will put two identities, one here and one here. So I will have k and k prime, and then I will have psi theta, k, k, h, k prime, and then I will have k prime psi theta at the numerator. Sorry. Well, anyways. And then I will do the same at the numerator with another k only. So I will do psi theta k. I will put only one identity here. So k psi theta. Okay. So if this is too confusing, I mean, but okay. So now, so these inner products are just the inner product between my vector and some basis state. So these are nothing but the coefficients ck that I wrote up there. So this is ck prime and this is ck star. Okay. So if you want, I can rewrite this as yes, actually, this is not the proof. Okay, but just one second. Yes, so okay, so this will be useful for later on. So let me just write it now so that it's okay, sorry. Okay. Right, so this is true in general, and we will use it in a second. So let me just rewrite this. So let me do something else, and then I will go back to the proof for the variational principle, okay? So now that we've done all this work, let me just finish it. So now I can write this as a sum over k. What I can do is that I can multiply and divide by psi k. Actually, k psi, okay? So I can rewrite this as psi theta k squared, because I multiplied by k psi theta, which is the complex conjugate of this. So I'm taking the square, okay? And then I'm writing this as sum over k prime of these matrix elements. And then I have k prime psi theta over k psi theta, because I multiply here, so I'm dividing there. And then I'm rewriting this, the numerator, I mean, just as the square of this number, because you see it's just the square. Again, if you don't like this notation, just write everything as these coefficients, ck squared. So these are just ck squared, and these are just the matrix elements of this matrix. Okay. Now, sorry for the little, but okay, since now we are here, you can see that I can interpret this expected value, as we call it, or this Rayleigh quotient, which in physics term is also known as the expected value of the Hamiltonian. We can interpret it as a statistical expected value, because you see that now I have an object which is positive definite, which is normalized in L2 norm. So I can interpret this as a probability density times something else, which is the quantity I'm taking averages of. So if you want, I can rewrite this as the expected value for K, which is distributed according to what we call the Born distribution P pi B of K. I will write it down in a second, of this object here, which we call the local energy. So let me maybe write down a few definitions, but it's just a rewriting, if you want, of what we have already seen here. So the Born distribution, you can read, it's written here. So it's this one, pi B of K is something that is proportional to, if you want, this thing. So K psi theta K squared, and this is the normalization, but I'm not writing down. So it's proportional to this. Or if you want, this is the same as saying that this is just Ck of theta squared. Okay. So if you want, now my Ck of theta, which is some functional form that I've chosen to represent the coefficients, these are complex numbers, remember. If I take the square of all these numbers, this will represent a probability distribution that we call the Born probability distribution. And the meaning of this probability distribution is that it will give us the, yeah, indeed, it's what I wrote at the beginning. So the square of these coefficients is the probability of observing, for example, that the spin up is one, the first one is up, the second is down, etc., for an arbitrary value of K. Okay. So K now is, again, is one of these 2 to the power of n possible combinations of the spin. So this probability distribution in this large space will give me the probability of observing one of the 2, or one of the 2 to the n possible states of the spin. And the local energy it's called the local energy for historical reasons. There's no specific reason why. Okay. Should be called like this. It's essentially just this object that you see written here. Okay. So if you want another way of rewriting this, is the following. So K H psi divided by K psi. It's completely equivalent because this is just an identity, so I can remove it if I want to. So think that the sum over K prime of K prime is the identity, so I can remove it. And then I just have KH psi, which is exactly what you have here. Okay. But still, this form is interesting because it tells you what is the cost of computing this local energy. And you can see that if now I fix K, the number of K primes I have to sum over in order to compute this local energy will depend on how many non-zero matrix elements I have for H. But what I told you at the beginning is that we have column sparse matrices, which means that I can just know a priori what are the non-zero K primes and just pick those and sum only over the non-zero matrix elements. So which means that computing the local energy for fixed K takes only polynomial time, provided that I know how to compute these numbers, Ck and Ck prime, also in polynomial time. Okay? So why am I telling you this? Because, as you can see, now we can interpret this Rayleigh quotient as the expected value over this probability distribution of something that is computable in polynomial time. Okay? And since I told you that this Rayleigh quotient satisfies this inequality, I can now minimize it, estimate it using, for example, the Monte Carlo procedure, or any sampling procedure that allows me to estimate this quantity, and then minimize this expected value. Okay, I will give you more details in a second. Yeah.
So, understand. So here, the local energies, you can compute it in polynomial time, but then you have also to sample, right? One column.
Yes,
so
yes.
It must be.
Yeah, so let me, yes, so okay, now I will tell you these details. Okay, so first of all, I mean, I promised you the proof of the variational principle, so, but I got distracted. I think you've seen this in maybe in some math courses, but in maybe in another form, but okay. So the proof is simple. So now what we can do is that we use another identity, resolution of the identity. So instead of using the if you want the basis states K, I can use the eigen states, eigenvectors of the Hamiltonian. Okay, so these psi K are just a set of orthogonal eigenvectors, and they are the eigengets of the Hamiltonian, eigenvectors of the Hamiltonian. Now, if I put these in exactly the same places where I put it before, now you see that the Hamiltonian is diagonal by definition in this basis. So I can write E of theta. So this will give me psi theta psi K, sum over K. And then I will have the eigenvalue. So H now in this basis. So we can use the fact that this H in that basis is now diagonal. So I will not write K prime because I already know that it's diagonal. So I will just have another psi K here if you want, psi theta. And then I will have the matrix element, which is just the eigenvalue EK. Okay, at the numerator. And then at the denominator, I have the same thing, but without the, so EK. So I can already write this psi theta psi K squared. Okay, so if you want now, I can rewrite this as sum over K of the square. So you see this is now the same number. It's not like before where I had the two inner products of psi theta psi K. So the inner product between my trial state psi theta and my exact eigenvector psi K times EK. And then I've divided by the same linear combination, but without the EK. So this is just the norm if you want. Okay. Now you see that the proof is done because now I have a convex combination of numbers EK. So this is a convex combination, which means that this will be by definition, and these numbers, right, are all in between 0 and 1 by definition. Okay. So if you want, I can write this as a linear as a sum over K of some gamma K EK, where gamma K are all in between 0 and 1. Right, so which means that now this is by definition now, so I mean, I can conclude that it is larger or equal than the smallest of these EK, which is at 0, it's 0. Okay? So this is the proof of the variational principle. Yes.
To understand, in the previous Blackboard,
yeah.
The important thing is that we can estimate E of theta with that expected value. This,
yeah.
Okay.
Yeah.
Because this is a quantity that we want to
minimize, yeah.
Okay.
To compute and minimize that. Yeah.
Okay, thank you.
And then here I will just going back and proving you that this is okay.
I have another question, which is, so is there some bound a priori of E lock?
No.
Okay.
But you can prove that the variance of ELOC is bounded.
Okay.
Which means that yeah, indeed the estimator is fine. The variance is finite.
Okay.
You can use all the inequalities that you.
Yeah. But even if so you don't have even that I don't know, the real part is greater than E0 or
The
something
imaginary
like that.
part is finite, but on average it's 0. That's the only thing you know. For example.
Okay.
Sorry, what was the question? The other thing?
The real part maybe is greater than E0 or something like that.
No, you can't. No, it
Okay.
can be lower than it's 0. The real part can be lower. Yeah.
Okay.
You only know that on average it's larger than it's 0.
Okay.
Yeah.
Thanks.
Okay, good. So now we have everything, all the ingredients that we need to do what people call variational Monte Carlo. So, and this was invented by Macmillan, Bill Macmillan, in the 1950s. Okay, so it's before the equivalent of Bayesian things that I'm just targeting. But anyways, no, because also I think there is something related to this also in the Bayesian context. But okay. I don't want to enter into that, but in any case, so variational Monte Carlo is essentially what I wrote you there. So it's this algorithm where you use Monte Carlo to estimate these expectation values. So for example, you use Markov chain Monte Carlo, you use Metropolis, whatever you like, or use other approaches to sample from your model. So you do essentially two things. First, you generate samples from this probability density PB of K. And remember that now this will depend also on my parameters theta, because the psi, if you want, the coefficients psi theta depend on theta. So also this probability density will depend parametrically on theta. Okay, I didn't write it here, but now I'm putting it back. So I generate a lot of samples from this probability distribution. So let me call these samples, I don't know, K1 up to K and NS number of samples. Okay. 2, I use these generated samples to estimate the energy, right? So this is E of theta. So which means that I will approximate E of theta as 1 over the number. So just the simple mean over this over these samples of the local energy that again can be computed exactly, I mean, and efficiently if you want. Okay. Great. So this is one step just to estimate the Rayleigh quotient. Now you can show that you can also estimate the gradient of the energy using the same samples. So I will write the final formula because well, or I can derive it. I don't know how much time. Yeah, maybe I can just derive it just for a second. No, I thought you were disagreeing. Okay, so I don't have the demonstration, but I think I remember it. So so let me convince you that you can also estimate, if you want, the gradient with respect to my parameters of my of the energy. Okay, as some expected value over this distribution pi b of an object that I will call now G of K and theta. Again, these are such that K is sampled according to pi beta, pi b. Now we have to find out what G is essentially, okay? So
so can I ask another thing? So when you do something like this, usually you enforce the fact that your estimator E theta is real, or you don't care, you just look at the real part?
Yeah, we just take the real part, but you can.
Okay.
Yeah.
So I have one question. So maybe you will explain it later. I don't know. So you said you generate samples, no? But this means that you need the polynomial procedure to generate them, right? Because in general they could be exponential.
Right. Of course, yes. So this will depend strongly on what pi b of theta is. There are two philosophical things you can do. So the first one is that you pick a model you can sample from exactly. I will give you examples later. Or you pick a model that is more expressive, but you don't know how to sample from that exactly. And then you do Markov chain, Monte Carlo, or any other heuristic. There you don't have any guarantee of convergence, but we are physicists. Okay, so what's that?
You also do exist models that are sparse by construction, that are like polynomial by construction, or not? It's not.
You could use kind of methods, approaches, or if you that's what you have in mind, yes, but it's not well developed. Yeah. Okay, so now, so the proof of the gradient. So what we want to do is that we want to take the gradient with respect to theta of this expected value. Okay, so let me make the assumption that the state is normalized. So I'm assuming, so to simplify, that psi theta is equal to 1. That I can do if I pick my probability distribution to be normalized in L2 norm. Not always, but okay. Now, if I do this, so you see immediately that I can rewrite this as sum over k psi theta. So I put an identity here. So I have to take the gradient of this. So let me write like this: gradient with respect to theta of psi theta, h psi theta. So this is the derivative, if you want, of the first vector. Okay, and then I have plus psi theta h, the derivative, so the gradient with respect to theta of psi theta. Okay. Yes, actually, there is no sum over k yet here, so sorry. Okay, just like this. So this is just the derivation. I mean, just the derivative. Okay, great. Now, now we put the identity. So I was already skipping one step. So I put an identity here. Okay, and then I have I don't know k h psi theta. Okay, plus the complex conjugate essentially. So let me not bother too much about this. And now we use essentially the same trick used before. So the log, the derivative of the log trick. So the log, how it's called okay, anyways, you understood. Because what we can do is that we can multiply and divide by psi k. So I can do this. So I can write this as psi theta k. Okay. Then okay, I just rewrite this other term. Then since I multiplied by this, I have to redivide by this. Just 1 second. Yeah, sorry. So actually I'm multiplying by its complex conjugate. So k psi theta. And then I have this derivative here. Okay. Okay, and now I can write this as the derivative. So I can write this as the derivative of the log of psi star. Okay, so that's why there is a times psi star. Okay, so I will write this as the derivative with respect to theta of the log of k psi theta times k psi theta. And then I also have the complex conjugate. Okay, so this is the only this log trick. Okay, so I'm writing this as the derivative of the log times the function itself. Okay, and now you can see that I've reconstructed exactly, I mean, something similar to the form that I had before, because I have now the square of this coefficient. So I have sum over k of k psi theta squared, and then I have this is the local energy, okay, times this derivative of the log. So I have so the complex conjugate. Okay, so I have the local energy of k times an object that sometimes we call dk, so star because it's complex conjugate of k, plus the complex conjugate. Okay, so what is dk? Dk is just, it's written there, so dk is the sorry, yeah, the k is not the right, so right, so d is the, so let's say called dl. So it's dl of k. So this is the derivative with respect to parameter L of the log of my coefficient, if you want, ck of theta. Okay, which if you want is exactly this object here, star, right? Because you see that it's the complex conjugate of that. Okay, so finally I can then write all of this as the expected value over this probability distribution dB of sorry, pi b, the same distribution that I was considering before, of the local energy times this d star. But I also had the complex conjugate, so actually I have twice the real part of this, so twice the real part of this. Okay, so if you want the expected value of twice the real part of that product. So as long as I'm able then to compute the gradients of the log of my coefficients of my model, then I can compute also efficiently these gradients. So which means that I can then go back to my algorithm here. And for example, I can go to step 3 and update, I mean, I can do a gradient descent, as you can imagine, so I can update my parameters at the next step, let's say L plus 1, to be the old ones minus eta, you know, this G, this estimate of the gradient that I can call, I don't know, G at the step L. Then I have to go back because my model has changed, so I have to regenerate samples from this new model, re-estimate the gradient and the energy, and then until I will converge. So this is what we call variational Monte Carlo. Yeah.
I have a question. So this G is just a sample from that G, or you do an average of?
Yeah, sorry. So G, yeah, I use the yeah, sorry, I'm abusing a bit notation, but this is G L if you want. This is G, my vector G is just this gradient. So let me call this, so the per sample is let's call the per sample G, small g, and the average of the gradient is capital G. Yeah, which is consistent with the notation, I think, of the first hour, maybe. Okay, so if you want the per sample G is this one. So this is the G of K and theta. So the per sample G is just the local energy times the star, twice the real part of this. It's the thing that you average over the distribution. Okay. Okay. Great. So now, what is? I mean, you can see already where I'm going. Maybe because what we can do is that we can introduce a parameterization of these coefficients in terms of a neural network. So this is what I call neural quantum states. Quantum state, okay. Yeah, indeed, the idea is that I have now these coefficients Ck of theta, which again are just a rewriting of these, if you want. I mean, they are all equivalent ways of writing them. So, and I just parameterize this with some artificial neural network. For example, a feed-forward neural network, as I wrote you this morning. You can just also think that K is a vector of these n numbers, plus or minus 1. I mean, I'm calling K just an integer for simplicity, but it's just a vector of inputs that can be plus or minus 1 in this case, binary inputs. Yeah, so this is, yeah.
So sorry. So they are not K different functions. They are really a function of K.
Right, yes.
Okay.
So, so indeed, maybe this notation is a bit confusing because of that. But so what is, so this neural network? So this neural network will take as inputs these quantum numbers that I also wrote like this at the beginning, I guess. So this can be just plus or minus 1 each of them. So we'll do whatever you need to do in the network, and then we'll have only one scalar output, which is for this given choice of K, which in this case means just one of the 2 to the power n possible states. It will output these amplitudes. Okay, so this f of, if you want, I can also write this as sigma 1z, sigma 2z. Okay, so this is the game here. I have a parameter that computes for me this Ck, so this the components of the vector in this huge space. So I never store the components. I just ask the network to compute for me the components that I need to sample or to estimate the local energy. And essentially, that's it. that's the parameterization that we introduced in 2017. So there's a paper. Okay, so this is the main parameterization that we use for this kind of problems. And then you can ask all sorts of more detailed questions. So for example, one peculiarity of these representations that makes them different, if you want, to probabilistic modeling, is that these f's, if you want, these coefficients, so these are all the same thing, are complex in general. So these are not, if you want, probability densities and in standard probabilistic modeling. But what is a probability is the square of these coefficients. But unfortunately, we need also the coefficient themselves with the phase to compute the local energy, for example. So in the local energy, the phase will enter, whereas in the sampling, they will not. So one peculiarity of these architectures that we use, for example, that they must output a complex number. So there are different ways of dealing with this. And I have to say that the mathematics of complex neural networks is poorly developed in general. So if you have some spare time, maybe it's good if you think about these problems. So there are two alternatives to work with complex neural networks. Complex valued artificial neural networks. So the first one is that you use completely real valued weights. So let me call now this again f of k and theta, and I take my thetas now to be real. As in standard applications, if you want, of neural networks. But now I will parameterize these, if you want, in polar, for example, in polar form. So for example, a to the I phi k times some amplitude a k. So which means that, for example, you can just take a feed-forward neural network with two outputs. So the first output will be the phase of the neural network, and the second one will be typically the log of the amplitude of the wave function. So the log of this ck will be, so it's the same that you know typically also with when you parameterize probabilities. You never parameterize the probability, but rather the log of the probability, because it makes more sense. And you can see that yeah, I mean, it's the same story here essentially. Actually, yeah, most of the time we do this, we parameterize the square root of a, because then the square of this corresponds to this Born distribution. So then it's clear that it's the same. So first possibility. Second possibility, which is crazier, you work with complex weights. So second possibility, theta is are complex numbers in general. Which means that you still have only one output, because your output will be complex valued, but you have to be very careful because you can't work with arbitrary activation functions. You need to work with activation functions that make sense in the complex domain, right? So for example, the kind of activation functions, how did I call it? I think this morning I called them phi. So for example, the phi of x that we can work are, you know, all I don't know, for example, I mean, something that we use a lot is the log of the cosh of x for reasons that I will not enter into today. So this is defined for an arbitrary x complex or real. But for example, you can't use rectified linear units. So this is ReLU, at least not in the standard form, because the ReLU is defined only for real inputs. So if x is smaller or larger than 0, so you can generalize them if the modulus of x is smaller or larger than some cutoff radius. There are ways to do it, but out of the box, you can't just use ReLUs. So you have to think about activation functions that make sense in this context. And another thing that you have to be careful is whether when you take gradients, is whether these activation functions are holomorphic or not, right? And this is where all the fun happens when you start to use software that was developed by computer scientists who don't know what holomorphic means. Typically, there's been a lot of fun to pain more than fun to use, for example, PyTorch was not supporting complex numbers until very recently. JAX is indeed the software that we use, and it's the only one that from the beginning has had strong support for complex numbers and also holomorphicity and non-holomorphicity. But just to say that this is really a highly non-standard application that is not used in any supervised learning or unsupervised learning approach. So this was much less developed than we had hoped for at the beginning, but now this is good, well supported, at least by JAX and now maybe also by PyTorch. Okay, so essentially, yeah, I think that I will stop here because I didn't do the break during the thing, and I went a bit faster. And then with Filippo, you will see some applications of these. Or do you want me to add something specific that you think you will not be able to cover? I think I said more or less everything. If you have questions, I think that this is also a good time to ask them. Yeah, thank you.
Thank you, Giuseppe. So, question, comments? Sinho?
So if I'm understanding correctly, these methods are for when you have an analytical Hamiltonian and you just want to compute it on a computer. But I guess, like, what do you do if you want to compute the ground state of a physical Hamiltonian? Or it's
so there's no distinction, I would say, between these two concepts, in the sense that if you have a physical Hamiltonian, you always know, I would say, the matrix elements of that Hamiltonian. What do you mean by analytical? Just maybe, okay, clarify your question. So you mean that you know how to compute this matrix element efficiently or something else, something like that?
Okay, this question stems from my like confusion about physics. Okay. So I thought, like, when you like compute this like matrix element for the Hamiltonian, this corresponds to a physical measurement of the system? No?
No. The matrix elements correspond to your understanding of the interactions that appear in the problem. So, for example, if you have electrons and you have Coulomb interaction, right? So you know how to write down these matrix elements based on just the nature of the interactions. There's nothing to do, if you want, with the... So you know, that does not depend on... So there's nothing probabilistic in there. That's really the nature of the interactions. The thing that is probabilistic is only when you measure the system, and then you have this probability, this Born probability that plays the game of what you're going to observe.
I see. Okay, thank you.
So for all the physical problem or chemical even problem that we are interested in, we know these matrix elements. There's no problem there. The problem that we don't know, of course, the ground state wave function, so the ground state vector that is the lowest eigenvalue, correspond to the lowest eigenvalue of the energy. Yeah.
Other questions? Simone, you are looking.
Yes. So my question was, one was curiosity. So can you take as nonlinearity the exponential instead?
Yeah. You can. Yeah, the exponential is. The exponential is well defined. Yes, on the complex domain. So there's no problem.
Does it work well?
But the problem, of course, is that you want to avoid divergences and singularities. And if you work, this is indeed one other peculiarity of working in the complex domain, because, for example, log-concave has poles in the complex plane. So which means that if you're not careful during your optimization, you can easily have exploding gradients for no reason, essentially, just because you are close to a pole in the complex domain. So that's why sometimes it's better to work with this formulation, because here you don't have that problem. Even though, I mean, empirically, we find that these parameterizations are often more expressive for this kind of problems than these ones that completely decouple if you want the phase and the amplitude. So here, instead, everything is coupled together, so it's a bit better. So I would say that the understanding of these two is strongly limited, even mathematically, at the moment. So if you can help, it would be nice. Yeah.
Thank you. Before we have introduced the Monte Carlo variational algorithm.
Variational
right?
Monte Carlo, yes.
Exactly. But I don't understand. I don't understand what kind of problem does it address? That is, we use this algorithm for what kind of problem?
Yes, yes. So, so I gave you this example Hamiltonian, which is this transfer field dicing model. For example, you can use that to find the ground state of that model that describes some spins. For example, you take in some idealized situation, you take some materials, you freeze the electrons on some lattice sites in a crystal, then they can be described with this Hamiltonian. There is a lot of other problems, essentially all of chemistry. So all molecules that you see, all materials that you see around that can be solved with this approach. So we introduce this also in the context of chemistry. There are many other problems that are described by quantum physics. So essentially all the properties of electrons, of spins, I mean, all matter that is described by quantum mechanics, where you can use this method. And we have shown, and also many other groups have shown by now that there are several problems, especially in 2 dimensions, where existing approaches could not find accurate solutions, where these give you much better approximations, and these are now the state of the art to solve essentially these problems in 2 dimensions. And for example, Google DeepMind is also working on this, and they have a few people there working on applications to chemistry. And we are also doing that on our side.
Point of view, if I can add, from a practical point of view, the reason why you want to compute the ground state is because if you have an Hamiltonian, so a model.
E0, yeah.
Yes.
Yeah.
So E0 is the energy of a ground state. So the ground state, so the state with the lowest energy is essentially the state of matter at rest. Okay. And so you can use this to know what happens, what are the properties of matter at rest. We don't necessarily care about the energy, but we want to compute some then observable, some property of a matter. So is it an insulator? Is it a conductor? How well does it conduct? Is it a superconductor? So those are the properties we're actually interested. But first we need to find the ground state itself to compute them on top of.
So you can predict all properties of interest for matter at equilibrium.
Yes, just to like have a notion, what is the dimensionality you work for the input, like in a typical application?
Yes, so it depends a lot on the problem, but let's say there are already very interesting and challenging problems that happen when n is equal to 100 or so.
Okay, and what is the accuracy that you will get in such application?
It depends
more or less. Like...
So typically, it depends on the. It depends on the structure of the Hamiltonian, on the gap of the Hamiltonian. So, for example, if you have a gap with the first excited state, the first E1, let's say the energy, which is of the order delta, you want to resolve the energy of E0 with an error that is much smaller than this gap, this energy difference. So let me define delta equal to E1 minus E0. So you want an error, let's say epsilon, which is, let's say, much smaller than delta. The error on the E0.
Okay.
Or a relative error, actually. Yeah.
And is this approach also valid for nonlinear potentials? Like if the Hamiltonian has a nonlinear potential term, is it also valid, the approach, or is it limited to linear operators?
The Hamiltonian is always a linear operator.
Is always linear?
Yes. Yeah.
Because I thought that the Schrödinger equation will have this Laplacian term and then they have some potential.
That's the semi-classical version of what people call the nonlinear Schrödinger's equation is a classical approximation of Schrödinger's equation. But so the full Schrödinger's equation is always linear in a larger space.
Okay.
So the one that you have in mind is a classical, semi-classical approximation. That is easier to solve, but it's not the full thing. Yeah. Yeah, indeed, the quantum mechanics is all linear algebra in a sense. So it's an easy theory, much easier than electromagnetism or other things. But it's hard to solve because it's in a very large space. Yeah.
Sorry, can I ask?
Yeah.
But so for me to understand it better, basically this is the algorithm you present is a stochastic gradient descent where you leverage the physics of the problem. So you introduce ELOC and you do this.
Yes. So
the
okay.
idea rely on this. Okay.
So a very important point that I wanted to make here. So unfortunately, I already raised it, but as you can see, this is a very different setting than the supervised approaches that I showed this morning. Because in the supervised approaches, I had students essentially label for me ones and zeros in handwritten digits. But here, I don't have any student I can ask to give me the exact amplitudes of so the exact CKs that I try to learn and then generalize, because I don't know them. Nobody knows them, right? So instead, this is a completely data-free, if you want, approach, because the only information that I have are the matrix elements of the Hamiltonian, but these are given for me by nature, if you want. It's not something that is pre-labeled, or I don't know the solution beforehand. I'm finding it, if you want, self-consistently without using any external info. So it's more similar to a sort of unsupervised, or let's say even reinforcement-like approach, where you don't have any pre-solved, if you want, the problem, but you try to find it by yourself by minimizing some cost function. So in this sense, it's closer to reinforcement learning than much closer to reinforcement learning than to supervised learning.
So one question, because you introduced epsilon there. So do you have a way to certify or
yes,
see if you have an error smaller than a given threshold?
Yes. So something that you can compute is the so-called energy variance. So you can, on your state psi, you can compute this minus psi theta h psi theta squared. So if psi theta is an exact eigenstate of h, this is 0, because you have E0 squared minus E0 squared. Okay. So instead, if you are not on an eigenstate, this will be larger than 0 and positive. So in practice, if you are close enough to we can quantify this later on, but if you are close enough to the ground state, you can use this information over the expected value of the energy, essentially, to quantify it. So this would be the square root of this one would be proportional to epsilon. Well, okay, I have to check now the exponents, but some power of this will be proportional to epsilon. In some if you do some reasonable assumptions on how close you are to the ground state. But okay, so you can use this metric that you can estimate, again, just using the samples and an estimator which is very similar to the local energy. Actually, this is just the variance of the local energy. You can prove it. It's not straightforward, but this is just the statistical variance of the local energy. So now this tells you also that when you approach the ground state, this object will become smaller and smaller, because you are closing epsilon, so epsilon becomes smaller and smaller. And also the statistical variance of your estimator goes to 0, which is beautiful, because it means that the more accurate your state is, the less statistical fluctuations you have. So you can resolve energy differences that are really tiny whenever you approach So this is also the reason why in this approach, we typically don't need the tricks that people do in reinforcement learning, where you have a baseline reduction technique to reduce the variance, because here the variance automatically goes to 0 when you go close to the ground state.
And so that's really impressive. But in this way, you converge to one eigenvalue, right? So
yes, yeah.
You need some.
So of course, I mean, the whole business here is QMA hard, which is a complexity class that is essentially the equivalent of NP hard for quantum mechanics. So you can find the ground state in polynomial time, even with a quantum computer. But we can approximate it. I mean, we don't care if it's, but we can still, you know, try to find good approximations. And yes, you can get trapped into an eigenstate, an excited state for which this variance will be still 0. But your gradient then will try still to push you down. So it's a similar reasoning to the stochastic fluctuations, because you will have some noise that will try to escape, make you escape from this excited state. Yeah.
Other questions? So I may have one, or maybe a curiosity. So like the example that you gave, the Hamiltonian is like a finite dimensional, so it's a matrix. You are like, as you say, you are in a lattice.
Yeah.
But like when you go like to electronic structure that you have like the Schrödinger equation,
yeah,
I assume that like this representation that you have for these quantum neural networks will strongly depend in the way that you discretize the Hamiltonian. So I don't know,
yes,
can you comment a little bit, like how do you do when you are not in a lattice? Why this makes sense?
Now there's
like,
1 million details yeah. Okay, so when you have actual electrons that are not on a lattice, but they move in continuous space, you have to discretize space if you want to use this approach. Okay, or you can work directly with a wave function in real space. So I did the discussion all in continuous space, but there's nothing specific to, to discrete space, but there's nothing specific to discrete space. Actually, you can just work with a neural network that takes as inputs continuous variables, which are the positions of your electrons in a box. But then in that case, you have to make sure that this psi of R, now the positions of the electrons, must be antisymmetric. Because unfortunately, because essentially of Pauli exclusion principle, you know that if I exchange 2 electrons, psi must change sign. So then we have ways to enforce this antisymmetric property of the wave function by playing with determinants and neural networks in determinants. But okay, that's for another more research-oriented presentation, maybe. Yes. Or you can work directly with the Hamiltonian in discrete space. So there you don't have to put, if you want, this antisymmetry directly into the wave function, into the wave function. But then you have to pick a basis, so which means that then you have to take the limit of a continuum basis, which can be expensive typically. So there are these trade-offs. So either you work with determinants and you don't have the discretization, or you work in discrete space, but then you have to take the limit of the continuum, and this is typically more expensive. So at the moment, I would say that the approaches that are based directly on continuous space are more efficient for chemistry, especially. Yes, not for other problems in condensed matter where it's not clear. Yeah.
But like in those approaches, at least it's not clear to me that the variational principle holds. So you can parameterize and get a sub-solution for the ground state, for example.
Why? No, wait.
Because maybe the function that you learn falls down outside the space of your search space.
In continuous space, you mean?
In continuous space.
Yeah, okay. So in continuous space, you have to make sure that your parameterized state satisfies exactly all the boundary conditions. Yeah, but this we know how to do in most cases. I mean, I would say in all cases.
Oh, very nice.
Yeah. Yeah, indeed. If you don't do that, you can find anything essentially. Yes. Yeah.
So I guess we had a lot of questions.
Yeah.
If there is any, so very nice. So they really took seriously the advice.
Thank
so
you.
In this case, let's thanks Giuseppe again. Thank you very much.
Thank you.